Welcome everybody to the IETS IEA-GHG Joint Industrial CCUS Workshop. My name is Jasmin Kemper. I work for IEA-GHG. I'm a Senior Technology Analyst. And I'm going to hand over directly to my partner from the IETS, Tore Berntsson, who will give you an introduction to the workshop.
Thank you very much, Jasmin. And so, can you see my screen? You can see my screen?
We
yes,
can, yes.
Oh, yeah, sorry, yes. Yes, we have planned this workshop for quite some time because we have both our TCPs have high interest in the CCUS area, technologies and systems. Because they are among the most important measures for decarbonization in industry, of course. For both of our TCPs, TCP means technology collaboration programs, the CCUS technologies are of course central. We had a workshop together in Lisbon 2015, which actually was our first workshop in more or less this area. So we now feel it's very good time to have a new one and hopefully start more collaboration in this area. A background also is due to the need for deep decarbonization in process industry, a mix of novel and traditional technologies can be foreseen in many plants. And for that reason, improving the knowledge of design, integration and role of CCUS in process industry in a system perspective is therefore of very high importance for the introduction of these technologies in the industry sector. So that's the background, and therefore we have just the two following important aims. And that is to present experiences and important examples of ongoing projects in the planning, implementation and operational phases of such technologies in industry, with emphasis on design, integration and the role of these technologies in a system perspective. And also to discuss the need for further work, including opportunities for international collaboration between our two TCPs. Shall I, Jasmin, go on presenting IETS directly, or?
Yes, please go on.
Yes, okay, thanks. So now we are both presenting very briefly our two TCPs, and I start with IETS. IETS is Industrial Energy Related Technologies and Systems, and we were founded in 2005. We are actually the only TCP out of 40 around 40 within IEA working solely with industrial technologies and systems and all types of technologies and systems. So we are very broad in that sense. We have for the moment 10 member countries, as you see here: Austria, Canada, Denmark, France, Germany, Italy, the Netherlands, Norway, Portugal and Sweden. And we have 4 sponsor organizations from outside the member countries, from Finland, Ireland, Japan and Switzerland, and actually since 2 days a 5th one, namely US. So any organization not being within IETS can also join in with different conditions as a sponsor if you have an interest there. We work mainly with different tasks, and that is networking. We don't have money, so to say, to have calls and have joint projects. We more work with networking with different projects going on in our countries. And we have here 8 different big tasks that we are working with for the moment. I won't go through them in detail, but you can see here that they cover both different technologies and more and more during later years, also the system aspects of technologies in industry. We have, of course, also lots of workshops. This is one example of that. I will also mention that we will have our first IETS conference in 1 year from now. We have had several conferences and, as I said, many workshops, but in specific topics. And this will be the first general IETS conference, and we look forward to that. And we have lots of reports and topic sheets, which you can see on our website if you're interested. And we have also that you can also contact me, being the chair of IETS, or the vice chairs, or the secretariat. So very briefly, where do we see the importance of CCUS in industrial systems? I would base that on some findings we had in an international expert workshop we had in Vienna in 2019 with 50 invited experts. As you can see here, we at that workshop we covered more or less all different activities which are needed for a deep decarbonization in industry: technologies, systems, circular economy, innovation, policy, and so on. I will just show a few slides where we discussed CCUS technologies in industrial systems in more detail there. The technologies for a deep decarbonization in industry that we identified as the most important ones, and in which actually IETS now works more in detail with these different technologies. And that is, of course, carbon capture and storage utilization, CCUS technologies. And by CCUS, I mean both fossil and biogenic types of technologies and systems. We have also electrification in industry, and also including hydrogen usage. We have biorefineries, digitalization and artificial intelligence, and efficient energy and process technologies. And we discussed also very much the interplay and competition, so to say, between different new technologies that are needed for a deep decarbonization in industry. And we talked also about the industrial systems, where we need more methods for strategic evaluation of radical changes, which we call ex-ante evaluation, including also CCUS systems. Process integration and looking at consequences for CCUS in a system perspective in the energy system when you put in a CCUS in an industrial plant. And also strategic evaluation of industrial negative emission systems, for example, using biorefineries in industry with different bio-CCS types. And finally, we also discussed industrial symbiosis as a major measure for deep decarbonization, where CCUS systems will also be of very high interest and importance. And finally, industry in a circular economy, where we also discussed very much the CCUS systems role in circular economy and in novel business models also. Finally, I just would like to mention one task in which we work with CCUS systems, or will work. We are planning that task about circular carbon systems, our task 21, where we have had discussions in different workshops about sustainable energy system and circular economy systems, which are both contradictions and have synergies, and to identify how we can work with the two two ways of looking at industrial systems in order to identify a circularity of carbon, for example, and of decarbonization in such systems. And that has led to these two subtasks that we will work with, and anyone being interested can contact us in that case. Subtask A will be about circular carbon systems in industry, and that will be about modeling and in cooperation with another TCP, ETSAP, working with modeling of different system levels, and also integration of carbon capture in industry. There we have it specifically. Subtask B is industrial symbiosis, where we will work with definition and delimitation, practice examples, and business models, which also will include CCUS systems, of course. And there we have high interest from a number of countries, as you can see below there. I think that is the end of my presentation, Jasmine.
Yes, thank you, Tore, for the introduction. And now my colleague Abdulaziz will give you also an introduction to IEA-GHG.
Good afternoon. My name is Abdulaziz. Again, I'm a technology analyst with the IEAGHG, and I'm pleased to walk you through the mandates of IEAGHG. Firstly, the disclaimer. Next slide. Next slide. The IEA Greenhouse Gas Research and Development Program is organized under the auspices of the International Energy Agency, but is functionally and legally autonomous. Views, findings, and publications of the IEA Greenhouse Gas Research and Development Program do not necessarily represent the views or policies of the IEA Secretariat or its individual member countries. Next slide. These are members of IEAGHG, and I would like to seize the moment to thank these members for their support. Next slide. So who are we? IEAGHG is a collaborative international program founded in 1991 and is a member-based organization with strong membership involvement. The members meet twice a year to inform and decide on technical studies undertaken by the program. The technical reports produced are used by policymakers, but are not policy prescriptive. These reports are objective, impartial, and independent. Next slide. So what do we do? Although our mandates covers all greenhouse gas mitigation options, our current focus is on CCS technologies with a watching brief on alternative options. Through our technical network meetings and conferences, we facilitate the dissemination of the latest research and results in capture and storage technologies and encourage collaborations between groups. Our research is published through technical reports, reviews, and information papers. These are available free of charge to anyone within a member country or organization and can be found on the IEAGHG website. Through our involvement with groups such as CSLF, UNFCCC, and many more, and also attendance at the COP conferences, our technical reports are provided to policymakers to assist them in making informed decisions. Next slide. The primary activities of IEAGHG include funding research into development and deployment of CCUS technologies. IEAGHG has published over 356 reports on all aspects on CCUS. IEAGHG is also actively involved in international expert networks, which include risk management, modeling, environmental and social research, as well as cost expert networks. The flagship IEAGHG conferences are the GHGT and the PCCC, the Post-Combustion Carbon Capture conferences. The GHGT is the largest global conference on CCS. The PCC6 was held virtually last year in October and was hosted by the UK CCSRC. Another prime event that IEAGHG puts together are the International CCS Summer Schools. IEAGHG Summer Schools are the only CCS education program to have truly international spotlight, with locations moving around the world. The program has now taken place in over 7 countries, covering Europe, Australia, Asia, and North America. With experts attending from all over the world, the IEAGHG aspires its summer schools to include a diverse range of students from a variety of technical backgrounds. The IEAGHG Summer School now has over 550 alumni, representing over 50 countries, with many moving on to successful careers within the CCS industry and academia. And with that, I would like to say that I've been privileged to have attended the 2019 Summer School in Canada just before the COVID, and I'm proudly an alumni. Next slide, please. IEAGHG is actively involved and engaged in technical knowledge sharing related to CCUS with these influential groups. It involves reviews of technical reports for IPCC, and also IEAGHG had an influence at the London Convention, which clarifies and permits transfer of CO2 across borders. Next slide, please. IEAGHG has been an important player in the COP conferences, and at the COP26 in Glasgow, IEAGHG organized side events and activities. One of the side events was the carbonization of industries via CCS, which obviously is imperative in light of the net zero emissions by 2050. A second event was focused on CCS in emerging economies, and pathways for CCS development was discussed for countries that include Nigeria, Trinidad and Tobago, Indonesia, and India. Next slide, please. The GHGT conference, which has been running for more than 30 years, is returning for an in-person or physical attendance in October this year, and will be hosted by Club CO2 in Lyon, France. For more information, kindly visit the IEAGHG website or go to ghgt.info. Thank you for listening.
Yes, thank you, Abdulaziz, for the presentation. We will now start with the first session, and first some technical things. So we usually run through 2 or 3 presentations in one go, and then after that there is a time for attendees to ask some questions. So we would kindly ask you, if you have any questions during the presentations in the session, please put them into the chat or into the question box, and then we will put them forward to the speakers. So the first session, we are starting with Piera Patrizio from Imperial College London, and she will tell us about the status and challenges of industrial BECCS systems.
Great, thank you, Jasmine. 1 second, let me know if you see my screen. Not yet, I guess.
We can see your screen now, yeah.
Okay.
But not your presentation. So yeah,
Yeah, exactly. 1 second. Yeah, okay. I think I know where is it. Sorry. Okay. I think now you can see my presentation. Correct?
yes, we can see it, but not in presentation mode yet.
Yes. Fantastic.
Mm.
Okay, great. Well, okay. Thanks a lot for the introduction, Jasmine, and thank you for inviting me to present at this panel. So, sorry for my voice, I'm a bit sick, I don't have COVID, but just so you know. So, since I'm the first presenter, I thought that I would kind of like give a little bit of framework into the challenges and the status of integrating BECCS within the industrial sector and specifically within the iron and steel sector. So just to give a little bit of like outline of the presentation, so this talk today is driven mainly by the results that of a study that together with Niall McDowell I conducted for IEAGG, which was focusing on the potential development of negative emission technologies in different sector, including of course the iron and steel sector. So the plan for today's talk would be to kind of like show a little bit of the results of the techno-economic analysis that we conducted of the potential adoption of BECCS within the integrated routes for steel making, so the BF CCS or the BECCS routes, and then compare a little bit these results with the emission reduction that can be achieved within another important low steel production pathways, which is the direct reduction routes. So just to give a little bit of background into the challenge of the sector, I mean, I'm sure you're all aware that the iron and steel production process is responsible to of around 6 to 10% of global emission, depending, of course, whether we account for the emission associated with the energy requirement from these plants. One big challenge for the integrated route, so the route that actually relies on blast furnace and basic oxygen furnace for the production of steel, is the use of carbon-rich materials, such as, for instance, coking coal. And the fact is that we can actually substitute the fossil fuel that is used as a thermal energy in the blast furnace, so coal, with low carbon fuels, such as, for instance, biomass. But substantial emission reduction can only be achieved with the integration of CCS. On the other hand, we have another important steelmaking route, which is the direct reduction route that is already less emission intensive than a conventionally integrated steel mill. And in this case, we can think about substituting, for instance, natural gas with hydrogen that act as a reducing agent in the shaft. And in this case, we can kind of like lead to almost carbon neutral emission. Of course, we need to account for the emission also produced by the lime calcination, but in any case, the emissions are quite low, and therefore we can achieve this emission reduction without the need of CCS. So here is kind of like a graph of the two different decarbonization pathways that I just discussed. The idea of this techno-economic assessment would be to kind of like understand the potential for negative emission and the cost associated with adding two different levels of CCS of capture, let's say, within blast furnace in BOF steel mill, and compare this with the emission that can be reduction that can be obtained with the adoption of hydrogen in a direct reduction furnace. So just to give a little bit of overview of the process of steel making, I mean, we know it's a quite complicated process, and one of the main peculiarities is the fact that there are a lot of gases and CO2 sources that's all over the plants, and all of these CO2 sources, all these gases are available with, I mean, there are different levels of CO2 concentration within these off gases. In any case, let's say the main process step for the production of steel are basically the raw material preparation, so the production of sinter, lime, and coke. Then we have the production of iron in the blast furnace, the production of steel in the BOF, and then we have all of the downstream process such as the casting and the finishing and rolling. What is important also to notice is that to maintain the operation of the plants, we basically need an electricity energy, which can be provided by the off gases of the blast furnace and the BOF. And then there is a balance, let's say, of electricity that can come either by a connection with the electricity grid or by combusting natural gas. So in terms of integration, CCS integration, we know that the post-combustion capture can achieve two levels of emission reduction by either capturing CO2 from the flue gases of the hot stove and the steam generation plant, and this is the CCS main configuration, or by capturing additional CO2 from the flue gases of other processes, such as, for instance, the coke oven and the fire heaters and the sinter plant, which is the CCS max configuration. In any case, what is important to notice is, of course, that we need extra energy for the regeneration of the solvent that is used in the capture process. And this extra heat is around 0.8 to 1.2 megawatts hour per ton of crude steel. This can be, of course, supplied by electricity from the grid or by, as I said before, combusting natural gas. So in terms of emission reduction, these are proposed here, and there is also the breakdown of the different level of emission reduction and contribution by the different part of the plants. So the reference plant that we're looking at is producing around 1.7 CO2 per ton of crude steel, and around 1.1 of these emissions are actually generated by the blast furnace and the BOF gases. So when we actually retrofit this plant with CCS, we can achieve around 57 to 76 emission reduction, depending, of course, on the CCS configuration. And importantly, as is noticeable in the graph in the right, if the additional electricity is provided by low carbon electricity, such as this is the case of, for instance, the grid in Norway, which is quite low in carbon in emission, then we can actually reach 80% of emission reduction. In addition, when we use charcoal instead of pulverized coal in the blast furnace, we can avoid around 0.5 ton of CO2 per ton of crude steel, and which means that basically in the best case scenario, we're actually achieving negative emission in the range of 0.2 ton per ton of crude steel. When we look at the economic analysis, we need to account, of course, for the capital cost of the capture process, but also of the different variable costs that are associated with retrofitting CCS, retrofitting the blast furnace with CCS. So we need to bear in mind that we have additional heat that is required for solvent generation. In this case, we pick a kind of like a conservative estimate, which is around 3 megajoule of heat per kilogram of CO2 capture. And then we need to account also for the capital cost of, in case we are using natural gas for providing this, the extra energy, we need to account also for the capital cost of a natural gas combustion cycle plant. So this is the overall breakdown of the levelized cost of steel production in all of the cases that we are seeing before. So the benchmark price of crude steel is around $510 per ton of crude steel, which is kind of like the market price at the moment. When we add CCS, we are actually increasing the cost by around $110 and $150 per ton. And the capital cost of the capture process actually accounts for around 30% of this increase. Besides that, then we have all of the variable costs. Importantly, we have the cost of the biomass preparation, of course, because we need to have this in form of a charcoal. And then in the case of adopting a natural gas configuration, so assuming that the energy is provided by natural gas, we also have the extra cost of the natural gas combined cycle, which is not impacting actually that much because the big chunk of the cost is actually associated with the energy required. So Based on this analysis, we wanted them to compare what would be the overall emission reduction that could be achieved in the direct reduction route, so in the other dominant steelmaking production technologies. And here, I'm not going to go too much into the process specification in the case of direct reduction, but it's important to basically notice that our assumption was that instead of using natural gas as a reducing agent, we assume the use of hydrogen, which is provided by the electrolysis process. And we are not assuming to use green hydrogen, so hydrogen powered by renewable, but because we wanted to kind of like assess the benchmark level of emission associated with using electricity from the grid to produce hydrogen. So what is important to notice here, as we can see from the emission, from the bar of emission that we see, is that the reference plant is producing around 0.72 ton of CO2 per ton of crude steel, so much less than in the case of a blast furnace. And it's important to notice also that a big chunk of emission is coming from the electricity, because the process is almost completely electrified. So the two big emission reduction that can be achieved are, of course, in the as it is quite clear, is either by using low carbon electricity for producing hydrogen, or by increasing the level of scrap recycling. This is quite intuitive in the sense that the more scrap we recycle, the least heat we need for the least energy is required for ore heating, therefore less hydrogen, and therefore less electricity, especially when this is provided by high carbon grids. So just to kind of like compare the different routes, what we wanted to see was whether in which country, based on the existing carbon intensity of the electricity grid, would make more convenient to actually adopt the blast furnace and CCS route, or whether the HDR would make more sense. So from this graph, we basically see the three solutions with, so the HDR with different level of scrap recycling, either 50% or 80% in the different countries. And in this case, the CCS configuration that was assumed is a configuration with maximum capture. And what we can see is that the BF with CCS route is actually the one that achieved higher emission reduction in almost all countries, except when we assume that there is low carbon electricity available. So this is the case, for instance, of Sweden, France, Austria, and Slovakia. And so basically, especially for countries such as Poland, or with that are relying on a lot of, they are quite fossil intensive electricity, then it would a much better solution would be to retrofit the existing plant with CCS. So just to conclude a little bit, and then I'm very happy to discuss this with you in the following session. What we wanted to see was actually what were the challenge of these two routes, and what are the key parameters, and make one solution kind of like better in terms of emission reduction than the other. The conclusion of this techno-economic assessment was that both these decarbonization pathways present specific techno-economic features that challenge the integration of in the existing iron steel plants, specifically in the case of an integrated route. The fact that there are multiple of CO2 sources challenge the integration of CCS, and the maximum emission reduction achievable is around 80% in the best cases when we also consider low carbon electricity available. The availability of low carbon electricity is even more important in the case of the direct reduction route, and this is because the process is almost entirely electrified. And we also have to remember that there is another caveat that is associated with this type of route, which is the availability of low-cost electricity. This is because at the moment, if we consider, for instance, PEM electrolysis as the dominant electricity production, hydrogen production route, at the moment the process is quite expensive. There is significant capital costs associated with it, which of course might decrease over time once the technology is deployed at scale. But at the moment, having access to low-cost electricity is therefore even more important in order to make this solution economical as well. So with this, I conclude. I hope I didn't talk too fast. And I'm going to end my presentation.
Yes, thank you, Pia, for this nice first presentation. And we are now going on to the second presenter. If you have any questions for Pia, then please submit through the chat or question box. We will collect them. And the next speaker is Christine Jordahl from SINTEF. And Christine will talk about energy efficient CO2 capture in industry. Christine, the floor is yours.
Yes, I just have to find out how I present.
You should get a...
start sharing. It worked yesterday.
Yep.
So.
Yep.
Does it work now? You see my screen?
Yes, I can see your screen.
Perfect. Then I will start. I'll talk about energy efficiency to capture in industry. Not all industries. You see a short graphic abstract of my presentation here. I'll talk about cement and waste to energy and a short touchdown on heat exchangers after that. Let's see. There. But first of all, one slide on CCS and what's happening. That CCS is happening. It's happening in Norway as an example, but also in other places. In September 2020, the Norwegian government launched the Longship project, a public-private cooperation for a full-scale CCS project. You can see a map of it here up to the right, where we have CO2 capture from two industrial actors. It's the Norcem Heidelberg cement kiln and the Fortum Oslo Varme waste incineration plants, both in southeastern parts of Norway. The Fortum project is not yet fully financed. And then we have transport and storage with Northern Lights, which is the transport and storage operator. That's a joint venture between Equinor, TotalEnergies, and Shell. And interestingly, the CO2 storage capacity is over-dimensioned with respect to Norcem and Fortum. So there is space for other CO2 sources also. You first transport the CO2 by ship up to the west coast of Norway, and then with a pipeline out on the Norwegian continental shelf storage about 1,000 to 2,000 meters below the sea. And Norcem and Northern Lights are foreseen to be operational in 2024, and then we have to see about Fortum. Total cost is about 2.5 billion euros for investment plus 10 years operation. And the Norwegian state covers 1.7 billion euros of this. And the overall project development is by the state-owned company Gassnova. So you have more info on a couple of links here also. But I mean, the good news is that, okay, CCS is happening. Also in Portos, for instance. So very, very briefly, I'll touch upon CO2 capture technologies. We also heard a little bit about that in the previous presentation. But as we heard, CO2 capture will always require energy. It's heat and or power, heat for amines, for instance. So they mainly require heat and some power. And MEA has been like the traditional reference solvent, while AMP-piperazine was suggested in 2019 by IEAGHG, which was then said to be 27% more energy efficient for coal than MEA, for instance. And there are also several commercial actors, more and more. So this is technology that's commercially available. Two different amine technologies will also be used by Norcem and Fortum. Basically, you washed out from the flue gas. If you look to the right, you wash the CO2 out of the absorber with the amine, and then you regenerate the CO2 in the desorber by adding heat, typically condensing steam. Then we also have technologies like membranes and oxyfuel that essentially use power instead of CO2 capture. And there's also a variety of solid absorption technologies with pressure and temperature swing, where pressure swing typically use more power and temperature swing more heat, obviously. So heat and or power is what you will use. About integrating CO2 capture in industry, we know that different energy-intensive industrial sectors, they have different operating conditions, different types of processes. Iron and steel was one example in the previous presentation. And they deliver products or services that should be as little affected by CO2 capture as possible. So the starting point should be to define the industry operating conditions. And then you find or design the most suitable capture technology, whatever that could be. What I'm saying here, that start with industry, not with the capture technology. It may seem obvious, but it's a good rule of thumb to remember, because when you talk about the most suitable capture technology, you want to have the most energy and cost-efficient capture technology with minimum impact on the quality of the industrial product and minimum environmental impact. And there can, of course, also be other constraints in different areas. So there are some important questions to ask yourself about the energy and cost-efficient capture if you're considering it. So is there any waste heat available? If yes, this is a very good starting point. And then how much can you recover? How much can you use for CO2 capture? Because if you can do efficient use of waste heat, you will have an OPEX reduction. But you also have to look at how much space is there available on site if you're going to retrofit. For industrial CO2 capture, I believe we're largely, at least in Europe, talking about retrofit of CO2 capture, probably in many other parts of the world also. You need condition, compress, or liquefy the CO2 also. Do you have space for that? And also, is there sufficient power transmission capacity to the plant? You need power for CO2 compression and liquefaction. And if you are going to rely on a technology like membranes and oxyfuel, you will need even more power. So that's part of the considerations. And how can downtime for the CO2 capture retrofit be minimized? Because you don't want to disturb and stop making money more than necessary while you're doing the CO2 capture retrofit. So let's jump to cement production. About 6 to 7% of global man-made CO2 emissions come from cement. Sometimes even see 8% mentioned. So it's a big source of the human impact on the CO2 concentration in the atmosphere. And what's special about cement is that about 2/3 of the emissions come from the calcination reaction, right, where we break up the calcium carbonate to calcium oxide and CO2 and emit CO2. And then about 1/3 comes from the fuel. We have about 20% CO2 in the flue gas, so higher than from a coal-fired power plant. And many cement kilns are and have historically been to a large extent fired with coal, but they can also burn biomass and quite a lot of types of waste. I once was at a cement kiln where they could actually throw down a sheep or half a cow in the calciner burner. So they can burn car tires, bottle caps, and so on. So plastics. So but there is also normally very little waste heat available in cement kilns. So if you look to the left, I'll explain why. You have combustion at 2 points. So in the rotary kiln, where you sinter the clinker, have a flame temperature of up to 1800 to 2000 degrees Celsius. And in the calciner, you have temperatures up to 900 degrees Celsius. And these hot temperatures, well, it's used for the clinker burning, but also for preheating and pre-calcining the raw material before it goes into the rotary kiln. So a lot of heat is used in these calciners preheaters, and then you also use heat for preheating the raw material before it goes into the calciner. So normally not much waste heat available, but there are of course exceptions, like the Norcem CO2 capture project in Norway, where they will use an amine technology, which is a technology that uses steam for CO2 capture, and they have enough waste heat for capturing CO2. About 50% of the CO2 from the flue gases, or 400,000 tons per year, can be captured with waste heat. And this is possible because this kiln uses very dry limestone. But it doesn't mean if you look at Norcem and say, oh, they use amine, then we're going to use it and it's going to be just as well for us. It depends on the raw material and how the kiln is constructed. And then at Norcem, they will also liquefy the CO2 at the plant with intermediate storage at key, as talked about before. And then you can see the nice location you have here for ship transport of CO2. It will be transported by ship to an intermediate storage and then pumped down for permanent storage offshore Norway on the west coast. But there are quite a lot of other capture projects in the cement industry in addition. And there is a large variety of capture technology solutions under development in this sector. And my hypothesis is that this is because we don't have this waste heat available. So I found a list of capture projects listed by Global Cement last October. of various stages of maturity, of course, and they have indirect calcination, adsorption, integrated calcium looping, oxyfuel, and a couple of projects. Green sand wasn't really clear what the capture technology would be in Denmark, and there is also an enzymatic solvent, even a solar reactor, and there's a full list that also describes some CCU projects in cement if you follow the link. So there's a large variety of capture options here that's under development. It's quite exciting to follow. And then we go to waste to energy. And the main purpose of waste to energy when you listen to presentations, for instance, from Fortum, is that it's waste management. And then you have the heat and or power as a side product. Because combustion of waste without CO2 capture is in itself a reduction of greenhouse gases with perhaps 75%, because the alternative would be waste disposed in landfills that generates methane emission. We have about 450 waste energy plants in Europe and 750 globally, and the CO2 concentration in the exhaust is about 12 to 13%, like a coal-fired power plant. There are probably deviations in this number also. And a ton of incinerated waste generates, it's a range here, 0.7 to 1.7 tons of CO2, but 1.1 ton of CO2 on waste is a good rule of thumb. Because municipal waste is a very heterogeneous mixture. You have fossil CO2 largely from plastic that can be perhaps 33 to 50% of total CO2 emissions. And connected to everything is with the waste incineration is, of course, how much waste will we recycle in the future, how much will we incinerate. I won't go into this, but it's always part of the waste incineration discussion, waste energy discussion. So for CO2 capture, I will focus on solvents now for waste energy. You saw the picture before with the reboiler where we need heat. And then we can talk about steam regeneration for two types of waste energy plants. It would be the power plants or the combined heat and power plants. Power plants, pure power plants are probably more found in Southern Europe and areas where you don't have district heating. And the typical regeneration for amines could be around 120 degrees, and you would need steam temperature 130, 140 degrees for this. So ideally, you would extract the steam for the solvent regeneration at an intermediate pressure that matches the reboiler temperature. But this can be costly if you need to retrofit it, and the turbine is not necessarily very big. How would you do that? So Tore, when I prepared this talk, he asked me to present problems. So one problem, one situation to consider here could be, okay, can we extract steam at a higher pressure, even upstream the turbine if you don't have a very high inlet pressure of turbine, to adapt to an existing, it could also be a low pressure actually, to an existing extraction point. But if you extract at a higher pressure, you would lose power, but you would also save CO2 compression work if you can increase the pressure of the reboiler and dissolve at a higher CO2 pressure. So it would be a trade-off here. But there is a question about, how can we challenge technology suppliers and best practices about how to operate amines or perhaps also other solvents? And I continue that on the next slide also, because not all waste energy plants actually have steam on board. Well, some of them, and hot water regeneration could be something to consider, for instance, for both for combined heat and power plants with a back pressure turbine, but also definitely for the hot water and the district heating plants that just burn heat, generate hot water and heat district heating network. So if you would have, depends on the season, depends on the type of the network and so on, maybe 80 to 115 degrees out for a district heating network. And either from the back pressure turbine or directly from hot water from the furnace. Could we use pressurized hot water for amine regeneration? Or could we reduce the pressure in the desorber, go to lower regeneration temperatures, and maybe use the return water from the district heating, which is colder? Of course, you need a lot of water passing through the heat exchanger since you're not condensing steam. But there are descriptions of solvents that regenerate at 70 to 80 degrees in the literature. So it's about challenging the truths if you sit with your industry or waste energy plant, and start from the operating conditions of the industrial process, and how do we find a suitable capture technology for this. And another thing about waste in incineration, it's not only about burning the waste, having the heat for capturing the CO2. It is waste that we burn. There is a lot of air pollution control measurements there, and these need to comply with CCS. So waste incineration plants must comply with what's called the BAT-BREF waste in WI legal document, which is best available techniques reference document for waste incineration. So waste to energy plants have 4 years to implementing this document, the rules in this document from 2019. And this regards combustion performance, energy efficiency, emissions to air, water, noise, and in particular for the air pollution control and flue gas treatment, you have dust and particles removal, SOx, acid gases, NOx removal, mercury and dioxide furans removal. So that's, then you have one side, what do you have and what's going on now to implement. And then you have CO2 capture, which is, at least in Norway, or will be regulated. And there is a need to identify an energy efficient integration that is in compliance with these waste energy regulations. So you need to find the match here. Because this BAT document only very briefly mentions GHG and climate change. It doesn't really deal with CO2 capture. And CO2 capture technologies, due to degradation and so on, may have stricter requirements on DSOx and DNOx than what is regulated now. And there will also be requirements probably on, for instance, amine degradation product emissions. So in sum, when I discussed this with a colleague, he thinks that authorities will almost certainly require new operating permit for waste energy with retrofitted CCS plants. And then I will conclude by talking about heat recovery for CO2 capture and heat exchangers, about thinking new in this area, because if we can recover the heat and run a CO2 capture process, we can have low OPEX, right? But can we also reduce the heat exchanger weight, the size, the cost? We may have a restricted space for retrofitting CO2 capture with optimized design and new production methods. Because heat exchangers typically have a constant cyclic characteristic geometry along the flow, but fluid properties can change a lot in heat exchanger. I mean, you change the temperatures, obviously. So this means that a constant geometry could be suboptimal. And I will show you an interesting example here that I got from a colleague about optimized heat recovery from an aluminium production line, where we have this more, say, organic shape almost, where it's been designed for low gas velocity at the inlet from the duct, and then the cross section is varied to increase the velocity and the heat transfer. There's also issue about scaling and not having particles attached to the surface. And this has been produced with additive manufacturing, what's also known as 3D printing, because you can't really do this with traditional production methods. And then just throwing out the question, can we imagine or produce other heat exchanger geometries where the limit is for getting this compact heat recovery that can be compliant with, for instance, CO2 capture? So that was actually the end of my talk, except some conclusions that CCS, yes, it is happening now. It needs to happen a lot more, in particular after the IEA report that came yesterday. I think many CO2 capture technologies are available, so it's not a technical constraint there. Others are under development, and amine capture is the most mature. Sort of a general observation from my perspective is that you have to seek the good matches in pressure and temperature between the industrial process and CO2 capture technology, and try to avoid the inefficient process adaptations. And also challenge the truth about solvent regeneration, temperature and pressure, heat exchanger designs, and many other things. Because CO2 capture it started with the power industry with coal and natural gas, and then the adaptation to in different types of industrial processes. There may be things we haven't thought about yet. So it's important to have a good dialogue here. I think that was it from my side. So thank you very much for your attention, and I understand the questions will come after the next presenter.
Yes, thank you very much, Christine, for your presentation. If you have any questions for Christine, please submit them in the chat, and we will deal with them in the Q&A session later. And we are now going on with the next presenter is Philip Johnson from Chalmers University, and Philip will talk about the implementation of CCS and BECCS in industry from the Swedish experiences with research and policy.
So yeah, thanks a lot, Jasmine. Can you see my screen now?
We can see your screen. Do you also want to turn your camera on so we can see you?
Where is the camera? Let's see. There. Oh yeah. So now.
Yes, excellent.
I should get it in presentation mode here. Let's see. There. You see it in the correct mode now?
Yes, we see it in presentation mode.
Okay. Yeah. Thanks. Thanks for inviting me. So I'll talk a little about implementation of CCS and bio-CCS or BECCS in industry and some experiences from Sweden, from research predominantly, but also say a little bit about the Swedish policy. So I'll say a bit about the Swedish context for CCS, give you something about the potential for CCS and BECCS on Swedish industrial emission sources, and give an example of how CCS can be integrated in industry, and then some ongoing work on the infrastructure analysis, transport and storage, and then also a little bit about total CCS potential in Sweden, and also say, as I said, a little bit about the policy context in Sweden. So what is a little bit special with Sweden in a CCS context is that we have our climate targets, that net zero emissions by year 2045, and we also have a substantial amount of biogenic emissions. So therefore, bio-CCS or BECCS has been identified as one of the so-called supplementary measures to compensate for hard-to-abate sectors to offset those emissions until 2045, and thereafter also to contribute to reaching net negative emissions, which is also something that seems to be required globally, of course, because we probably have emitted too much to meet the Paris Agreement. Also, the Swedish Energy Agency has been appointed a national center for CCS in Sweden. So there's a lot happening on CCS in Sweden right now. So yeah, as I said, we have Sweden is an industry country, although it's also have a lot of rural areas, and there are therefore a lot of large point sources of CO2 emissions. So on the left panel here are those less than 500 kiloton per year, and on the right hand side those exceeding 500 kiloton per year. And those are what differs to other countries are that we have a lot of pulp and paper emission sources. Then we have refinery, chemical, steel, iron and steel, cement and power and heat, and all those, of course, could potentially apply CCS on then fossil emissions and or biogenic emissions. As for now, steel industry has chosen another track. It is a hydrogen-based steel, which is, you may have heard about this hybrid project. And going back to these targets, there are these governmental targets. So that is by year 2030, we have targets for bio-CCS, and that's up to 1.8 megaton per year by year 2030. And as defined in a public inquiry that was issued some years ago. And then by year 2045, 3 to 10 megaton per year. And the reason for the large span is of course that it's not known how well other measures will succeed until then. So this is certainly a challenge, because these in 8 years until 2030 we would typically require, say, 4 to 5 plants, full-scale plants to reach 1.8 megaton per year. Of course, depending on what emission sources one target for bio-CCS. We have both combined heat and power, like Stockholm Exergi. There will be a talk by them, I think, later today, and they are sort of quite far ahead in planning for this on the Stockholm plant, combined heat and power plant. Then we have the Cementa in Slite, also planning for CCS, and then we have refinery at Lysekil, which I will come back to. And then of course these other ones are just sort of symbolic in the sense that there will be a mixture of we don't know yet which plants will apply CCS, but the district heating sector has recently completed a project defining how could CCS come into play there. Of course, we depend on Christine's country here. That of course both from technically there are these two plants that are in the pipe in Norway in this part of this landscape project, also for transport and storage. So obviously those will be very important both for the technology for I guess for Cementa, also for some of the other experiences, and of course that the prime target for Sweden is also to store the CO2 in Norway. So if we just look at here are the here's the sort of the storage illustrated in the North Sea, geological storage under the seafloor, and here are again these large point sources, the largest one above 500,000 tons per year. If we from those ones take out the largest industrial ones, those are 28. So those are a cement plant, chemical plant, 3 refineries, 20 pulp and paper plants, and 2 steel plants, including a combined heat and power plant burning the off gases from blast furnace. And if we apply CCS on those plants, we have made a study a couple of years ago. Some of you may have seen it already, but where we, based on process modeling, sort of extrapolated, looked how it would be for all these different stacks in these plants, because some of them have several stacks, like refineries. Then we obtained this type of marginal abatement cost curve. So on the here axis here, you can see the sort of estimated cost in euros per ton of CO2. And here on the x-axis, you can see the cumulative amount of CO2 captured possible from those plants, assuming typically 90% capture rate. The reason there are more than 28 bars is what I said, because of this, that there some of plants have more than one stack. And the green bars are biogenic emissions, and the gray ones are fossil. So you can see what is sort of unique in Sweden is that there are actually more biogenic emissions that would be sort of more cost efficient than the corresponding fossil emissions for CCS. So that would mean if one would reach the same amount of CO2 captured using only fossil emission sources, it would cost more. The dotted line is sort of a rough representation of what it would cost for transport and storage. So this means that together they are, you could of course arrange the transport and storage system differently, but say that the total cost would be somewhere around 80 euros per ton, up to say 130 euros per ton of CO2, 140 euros per ton of CO2. And this could be compared also to the total Swedish CO2 emissions, all sectors, which is about a bit more than 41 million ton or 51 million greenhouse gas emissions. So that's actually roughly half of the total CO2 emissions that could be captured by CCS. So that in that sense, it's quite significant, of course. If we zoom in as an example of one of the Lysekil refinery, we had a project where we, together with the partners here below, Prim, of course, owns the refinery, Sintef, Christine's place, and Aker Carbon Capture and Equinor made also both a demonstration of post-combustion on the hydrogen processing unit and also research on what it would cost to apply CCS extensively at the refinery. And here is an examples of opportunities for heat integration on the refinery. So here actually in the lower plot here you can see 4 stacks, the hydrogen processing units, fluidized cracker, and then there are 2 sort of collection stacks that collects emission from various sources. And these are about a substantial part of the total emissions from the entire refinery. And you can see that there are residual heat that could cover a fairly large amount of the total energy required for the capture. But then, of course, beyond a certain point, we need external energy supply, which could be both existing sort of on the site, but also new capacity added. This will, of course, result in a cost curve for the steam that, of course, is reduced. The more, of course, obviously the residual heat you use, but then slowly increase the more you try to use the existing capacity, and then ultimately that you need to add external heat. And from this analysis, heat, of course, for the capture, and then we have the CO2 conditioning, and then, of course, we have the shipping and storage as the whole sequence here. But if we summarize this, we could say that the results show that the use of residual heat at site could supply around 40% of the heat required to capture most of the CO2 emitted today from the Lysekil plants, and saving around 30% of the annual CO2 capture costs in an amine scrubbing case that was investigated here. Despite the heat integration, you can see on these 2 bar plots here, the brown color here, the heat supply cost still dominates the CO2 avoidance cost. And here the avoidance cost is the entire cost, including capture, transport, but excluding storage. And we can mitigate around 1.5 from this analysis megaton and the total refinery emission, depending a little bit about the plans of how they will expand the refinery into the future for biogenic production of biofuels. Will be somewhere below 2 million tons per year. One could, of course, also increase using heat pumps and electric boilers, and basically remove all requirements of fossil supply. And the cost with using this residual heat plus the external energy will be around 70 euros per ton for the capture itself, and then without that, only external energy would be around about 90 euros per ton of CO2. Then the testing, and this is just sort of reporting from the Aker carbon capture activities, was successful. A smaller capture installation on the hydrogen processing unit, where the special solvent offered by Aker carbon capture so significant improvements compared to the sort of standard MEA solvent. And then if I go to transport and storage infrastructure, we have an ongoing work where one of our PhD students look at these emission sources, how they could be allocated, transporting to hubs, so collecting the CO2, transporting them to harbor, basically, where we have defined several transport hubs. So for those inland, those will be transported by truck transport. So far, the only option included in the analysis. And then sort of optimizes, and then they will be transported by ship to the intermediate storage at Kolsnes in Norway for further transport out to for geological storage, as I mentioned. So here is this. Here's actually a marker. This was just a place where I went skiing the other week, and I couldn't remove it from the Google map. Sorry about that. It was a nice place though. And so these were 3 scenarios investigated, only looking at the biogenic emissions with a strict target meeting the Swedish targets at 1.8, as mentioned before, in year 2030, and 10 megatons. We took the upper one here at 2045, and then only fossil ones applied to fossil emission sources, and then this combination. And then we can see we get different sort of allocation of these and use of these different harbors for transporting the CO2, and with different ramp ups of these. Of course, these are an extreme ramp up, and of course we'll also make it to see if to put some limitations on that. So this is sort of an ongoing work showing how these can be allocated and become different cost effectivenesses. And here we can see a table, and I will not go into the detail, but we'll look at different, or the PhD student look at different varying, for instance, increasing the ship and truck fuel cost. And if one do that, one can see that, of course, the relation between the truck intensity, how many trucks per megaton of CO2 you need, consider that the turnover time in connection to how many capture installations you get will vary. So this is sort of a sensitivity analysis that is an ongoing work. I should mention then that we also have looked, and there is a great interest from the district heating sector in Sweden, where we look at a similar marginal cost supply curve. Here is a little bit different. Here includes actually the truck transport in this example here, and it's divided into CAPEX and OPEX. And here we'll give the same sort with up to, say, 17 or so megaton of CO2 from these plants, burning primarily biomass as fuel, but all biomass residues from the forest industry, but also waste to energy plants, as was mentioned and discussed by Christine in the previous presentation. And actually, if we add those together, we could see that in all, the CCS could take some 35 million ton per year at the cost, say, around or less of 125 euros per ton of CO2, which is a substantial amount, of course, of the Swedish CO2 emissions. I'm not saying that this would be, of course, there are other ways as well. I forgot actually to say when I showed this industrial marginal abatement cost curve that currently for the steel industry in Sweden, hydrogen-based steel is the preferred option, which there are intense projects working on, which is, of course, in the long run, a much more sustainable option. Finally, I just want to mention a new project which will study and take sort of a holistic view on what pathways the petroleum and the petrochemical industry will have towards meeting the climate goals, considering not only CCS, but also other ways to handle the carbon in terms of circular systems and so on. Will define different pathways towards net zero emissions. So if I sum up this, we have a large potential for both CCS and bio-CCS in Sweden. There are generally favorable conditions. We have coastal locations of many of these, the largest emission sources in particular. And we have, sort of say, access to Norwegian storage infrastructure, of course, depending on what their price will be, how much they will charge for the storage. And there seems in Sweden to be a rather broad consensus on the prospects and the need for both bio-CCS and CCS. The challenge is, of course, financing this. And of course, we have EU ETS, as you all are aware of, that the EU ETS prices have increased significantly over the last years here, and now I think at 80 euros per ton or so, although there are still free allocation remains. So that's hopefully maybe that will be revisited that in the near future. For the negative emissions, there is actually nothing really within the European Union, but in Sweden we have recently an issued reversed auctioning system where the state, the Swedish state, will give a guarantee for buying those negative emissions from bio-CCS. Other options would be some quota obligation for selected sectors that are hard to abate. BECS credits possibly in the EU ETS for compensating hard to abate sectors. Voluntary markets, we see some of those already for negative emissions for compensation, like in the agriculture sector or food industry, or other states as buyers within Paris Agreement would be possible as well. We have a paper where we discuss those that I have a list in the end of the presentation that will probably handle out, and you can have a look there. And of course, it's important to state that CCS is part of an overall mitigation portfolio. And in Sweden, we have ongoing work, governmentally supported work within something called a fossil-free Sweden initiative, where different sectors have established roadmaps towards meeting the Swedish climate goals. I should also, my last point is to still state that it's not obvious that, and I think it's important to remember that CCS is always the preferable option. One could say that CCS can be used in, or should be used in, cases where energy from oxidation of carbon is the cheapest way of covering the process energy. But therefore, it's important also to look at alternatives. For instance, as an example, hydrogen-based steel, but also considering future when there is limit, for instance, on biomass for hard sectors which would have difficulties in mitigating their emissions, where carbon-based fuels will be difficult to substitute, aviation sector and so on. So that most likely will result in increased competition of biomass, which may change the market. So that ends my presentation, and I have a list of publications that you can look at later when you get the presentation handouts. So thank you very much.
Yes, thank you very much, Philip. And we now have time for answering a couple of questions that some of you have submitted through the question box. So if our speakers from the session could please come online and turn their cameras on for this discussion. Thank you. So we have a couple of questions that we received, and maybe we are starting with Piera's presentation because that was the first one. And there was a question about how much could the capture plant benefit from significantly improved heat efficiency in the BF type steel mill.
Yeah, thank you, Jasmine. So we haven't looked specifically or what's the kind of like the benefit of increase the efficiency in this case, but in any case, what we noticed, what was the most important factor in terms of emission reduction, especially for the integrated route, was the fact that because of the different CO2 sources around the steel plants, the maximum level of capture could not be more than 80%, even in the best case scenario. So, I mean, I haven't quantified the contribution of increasing the heat efficiency, but I would say that in any case, it's difficult in the case of BF-BOF configuration to achieve like really low carbon emission, especially compared to another route.
Okay, and another question was whether you could clarify the source of hydrogen in the DR process. Did you assume that the hydrogen was produced using PEM at the same cost as hydrogen from natural gas would be? And did you also include the emissions from hydrogen production in the CO2 emissions analysis?
Yeah, no, so the economic analysis, which was not shown in the presentation, considered also the capital cost associated with investing in PEM, and so the production cost associated with using electrolysis as a technology for hydrogen production. And yes, we consider the emission associated with the use of electricity, and depending, of course, on the carbon intensity of the electricity that we are considering. We could, of course, have considered green hydrogen as a substitute, but the idea of this study was to compare the overall emission reduction that you could achieve from BECCS plants with HDR from hydrogen, because this is kind of like one of the route that has been proposed more in literature and is quite popular at the moment. And we wanted to have kind of like a sensitivity at country level for that study.
Mm-hmm. Okay, yes, thank you, Piera. Then maybe we can switch over for a question to Christine. You talked about waste to energy and all the permitting and regulations, and especially that there needs to be a match between the regulations. And do you see that there needs to be more research and also maybe an approach in communicating the benefits? Because we might need to have maybe a better cleanup for depending on what amine we are using, and that changes how deep you do decipherization or denox, but that would also then in the end probably lead into maybe better air quality regarding to the waste to energy plants. So how do you see what is needed there? What are the gaps? And
I think this is something that needs to be looked more into, yes, and understood, because normally you either work with air pollution control or you work with the CO2 capture and understand how this comes, because this, I actually used a lot of input here from a colleague who knows waste to energy and knows this BRF waste incineration, and got the input from that slide from his. I should mention Mikael Bessedan there. Yes, there's a lot of work to done there. We're doing a little bit in our work that is ongoing now. It's called the Access Project, and there's probably more things that could be done also. But to be aware, and mutual awareness is the first step, I think. And hopefully that this adaptation is ongoing now for waste incineration plants. This BRF waste incineration doesn't close any doors that would be useful or make it more costly for CO2 capture.
Mm-hmm.
I'm not sure if I can say more than that, but that's
yeah. Thank you. And then we have some questions for Philip. Philip, is there much potential for the geothermal energy to provide the excess heat that would be required for the CO2 capture process, for example, at the refinery that you talked about?
No, I mean, if you, geothermal energy, no, if I understand it correctly, I mean, the geology in Sweden is not that, there are some projects for geothermal energy, but it's not very well. We have a lot of solid rocks, and you need to drill very deep. So I haven't really heard anything about that as an option. So what I showed was residual heat from the process itself. There is typically quite much waste heat or residual heat in these kind of processes. So that was so no. The answer is
no.
Actually, I can quickly. There was another before that one was about if the BECCS implementation in terms of energy capacity and emission reduction, and if oil and gas companies. I think when you look at the global modeling, in order to stabilize, according to the Paris Agreement, some of these, depending on how bad or good we are doing, show tremendous need for negative emissions. But of course, there is still very little actual projects, I would say. So maybe in that sense, Sweden is a little bit unique. We have these very many of these sort of concentrated biogenic emission sources. So there are some other. There's been an ethanol project in the US and so on, but not much, I think. Then maybe the question about whether if the Norwegian government agreed to take the liability for the stored CO2 when the sites are eventually closed, considering this is a cross-border transport of CO2. So maybe Christine can comment that, but I, of course, as far as I understand, it will be, we just happily ship it to Norway, and they do this as a business case. And I hope Christine and her will take responsibility for that. That's my understanding. That the storing organization, the storing country, will have to do this.
I'm not a storage expert, so I can't say this in detail, but if I say something out of memory now, it may be wrong, but this must have been thought of.
Yeah, yes. And this session is recorded. But I think it actually that, but I'm not 100% sure either. I think it's a good question. And then there was a question about the factors, the timeline showing the facility industry that will, for that, when I showed this infrastructure, that was from a mixed integer program exercise where it sort of minimized the cost over the time period shown. The more artistic illustration I had in it, that was just random, so to say. That was just for illustration. And then there was a final question, if we have considered options besides ship and truck. And no, as I said, for the time being, this exercise is only shipped from the harbor, these hubs, which is realistic. That would most likely be the case, to this place in Norway where they have this intermediate storage. But on land, we have so far only looked at trucks. Trains are a bit difficult because it's a lot of logistics and very fixed which train lines are available and so on. So that's something we will look at. There could also be waterways, canals, and so on, that we have some of those. So yeah, those I think were the questions.
Yeah, and then we had one last minute question coming in that probably also Christine can answer because it's relevant to waste to energy, about how to properly account for the biogenic emissions, given that they are mixed with fossil emissions and then they are kind of captured together. And what does it mean for the accounting?
It's only the fossil emissions that go in under EU ETS. It is possible to measure the share of fossil and the share of biogenic CO2 in the flue gases. Actually, you do that with a carbon-14 method. So you have a different concentration of C14 in fossil and biogenic carbon that is burnt. I don't think it's mandatory, at least not today, to have this measurement online. But for instance, on the local waste to energy plant here in Trondheim, where I live, they have measured it for a while, and then they have a sort of a typical distribution between fossil and biogenic CO2 that they report. Yes, but it is possible to measure. I think that's the most important part.
That's you. Okay, then thank you for your presentations and also for answering the questions. We will now move on with our second session. And the first speaker for the second session is Jan van der Stel from Tata Steel. And Jan will tell us about steelworks pathways to decarbonization and how that can contribute to a sustainable future. Jan, I think you might be muted. We cannot hear you.
Okay, now that's
now
done.
We can hear you. Yes.
Thank you. Now, again, good afternoon all. I'm Jan van der Stel, and I work for Tata Steel Research and Development in the Netherlands. And it's a pleasure to present to you all, let's say, Tata Steel's pathway for decarbonization and for a sustainable future. Okay. Now I will give you an outline of my today's presentation. I'll give you a short introduction, an overview of the energy systems we have on integrated steel sites, which perhaps gives you an answer to some of the questions just raised, some process optimization, and then let's say the impact of a major configuration change that there is a hydrogen-based DRI application. And then I end up with a small summary. This is how our steelworks looks today. We have coke ovens, we have sinter plant, pellet plant, 2 blast furnaces, a steel plant, and we have the mills, and all the works arising gases, which was also mentioned in the previous presentation, are at the moment utilized either in the blast furnaces for heat utilization, or are transferred to power, or are utilized at the hot strip mills, as mainly by the coke oven gas. And on the top you see that we have the Isanna plant installed. Now, and as an introduction, I'll show you that, let's say, the steel sector is a very energy-intensive sector, but, let's say, driven by higher energy prices and major process and efficiency improvements. Let's say the specific consumption came back by more than 60% since early 60s. And this has been done by a reduction of energy consumption, by reducing direct losses, by utilizing sustainable energy sources where possible, and a major thing is by process optimization. Now, this is driving, let's say, the steelworks, and how can we move this forward? If you look at the IJmuiden site, what you see is that most of the energy which is brought onto the site is coal and coke, and that is a big part is not used as an energy, but is used as a reductant agent in our blast furnaces. Then we have heat in the blast furnaces, and for the rest, let's say, the coal and coke is transferred into gas, which is put into the gas grid of the site, where it is being used as in the boiler systems, in the power plant for electricity, and for the heat up the gases at the blast furnaces. And also a considerable part of natural gas is used on the site. Now, if you look at Taat Steel in IJmuiden, where we look at the World Steel reporting, there you can see that Taat Steel is more or less ranked in the top 3 on the second place. If you look at carbon intensity, so that means that already a lot of work has been done in the world of lowering the CO2 emissions, and there we are let's say we are nearly at some thermodynamics minimums to achieve this. Now, let's say then the steel plant can do, let's say, is faced to further CO2 reductions, and that can be done by a further reduction of carbon sources as an energy source. We can reuse the carbon and store, let's say, carbon via CCS route or via CCU routes. And secondly, let's say we can also avoid carbon, and that is then changing reducing agent, where we apply then electricity and hydrogen and some biomasses that can be seen on the, let's say, on the last row. Now, let's say the decarbonization routes for the steel industry. If we have efficiency improvement, which is carbon based, that let's say then you can the outcome is that you use less CO2. You have CCS and CCU, again carbon based. Let's say you store or you convert the CO2 to reduce it. From coal to natural gas, then you make less CO2, and from coal to electricity via electrolysis and hydrogen, then you do not make any more CO2. So that means then, let's say, these 4 routes could be seen as the future for the steel industry. Now you have to distinguish in the steel plant you have the direct and indirect emissions. Of course, you have lots of indirect CO2 emissions by making electricity for the steel plant, which also give you CO2. And of course, at the steel plant itself, you have the direct CO2 emissions. Now, if you make use of the ways and means to reduce the CO2 emissions, then let's say what you see is that all those routes you will imply, like electricity, wind, solar, then that will mean that the electricity usage will go up as well in the direct emissions as well as in the indirect emissions. The decarbonization options can result in a huge increase of the power requirement, as said, and for the direct emissions, and that means that if you have CCS, CCU, natural gas, hydrogen, and electrolyzers, that means that the direct emission reduction could be between, let's say, 60 to 70% for the natural gas route to 100% for hydrogen application or electrolyzers of iron. But nevertheless, you will use an extra huge amount of electricity. Now, let's say you have the reduction potentials. We looked at that for, let's say, for some countries, for the Netherlands, UK, and for Sweden, and we found out, let's say, that the CCS will have the highest emission reduction in 2030, and that the let's say if you apply hydrogen and natural gas and CCU, that there are all kinds of restrictions which can be seen, but they are in the future be applicable. Now in Europe, we look at CCS and CCU projects, and we looked at the reports of ZEP, and we found that there are at the moment roughly 42 CCS projects, 8 CCU projects, and in the steel industry you have, that is at the moment, 2 CCS projects. They are located around at the North Sea, and also 3 CCU projects, which are mainly based on making ethanol and methanol. And the methanol project, that is a EU-funded project by where Tata Steel works together with SSAB, TNO, and Swerim from Sweden. And in this project, we use the stepwise development of TNO and Swerim to transform the CO2 into a methanol product, and that methanol is then be used as a fuel in and that can be used by a ferry, and that has been demonstrated in this project. So this is an initiative which is already been demonstrated. Now, what is Tata Steel doing at the moment? Tata Steel chooses for hydrogen-based steel making in the Netherlands, so that we have a green steel in a clean environment in IJmuiden before 2030. And the green steel is the steel sector of the future, we think, for sustainable construction, sustainable transport, sustainable energy, and in everyday sustainable works. Building this hydrogen economy and accelerating the energy transition, it will be necessary, let's say, that large amounts of hydrogen will become available. And this whole concept is based on DRI technology within a period of 8 years. And there, indeed, which has been said, still some CCUS might be necessary for further reduction of the CO2 emissions. Now, what is the current operation in that? Is that we have, as I said, we have blast furnaces, we have the steel shop, where we have the caster, then we have the rolling mills, and in the new concept, let's say we will change in one of the blast furnaces routes with a DRI plant and an application of electricity to make a hot metal for the steel shop. But let's say that means that the front end will more or less remains the same. Now, using hydrogen for direct reduction, there, let's say, then you will have an electric arc, you will have an electric steel making facility, and there hydrogen is the main reducing agent. If you go to pure hydrogen, then that will be the main agent. On the other hand, if you have people, if you have systems where you also apply parts of natural gas, then also this can be used. This is all the hydrogen technology is at the moment, especially based on natural gas. It's a mature technology and is distributed around the world, mainly at places where there is cheap natural gas available. We have then you will have very lower CO2 emissions compared to the 1.8 kilogram per ton of hot metal when you use this DRI applications. And at the moment there is one plant in Europe. That's the ArcelorMittal plant in Hamburg, and of course, which is also mentioned previously, that there is a pilot plant facility at Luleå at the hybrid project. And Tata Steel's strategy is, let's say, to make in 2030 2.7 million tons per year. Now, then you have the transition to 2030. Now we have a sinter plant, coke plant, and 2 blast furnaces, and within 2030 we will have a DRI plant and melting units instead of one of the blast furnaces. And in 2015, this could be changed into that the electricity comes from green power and hydrogen is available. Sinter plant is mothballed or stopped. We only have a pellet plant, a DRI plant, and melting units. And perhaps we have an Haisana type of system, which is a smelting reduction plant, which can be used for the reverts in the circular economy part. So this is Tata Steel's decarbonization strategy towards 2030, and that is then based on a hydrogen steelmaking. And in this transition period, natural gas will probably be used for the DRI production as long as not enough sufficient hydrogen is available. And in this transition period, also the CO2 emissions will substantially be reduced. And CCUS will play a role in this complete decarbonization strategy. And sustainable steelmaking includes not only a climate change, but also a change in raw materials usage, environmental impact, and product circularity. And the combination of these technologies will be needed to fulfill all the sustainable goals. Thank you for your attention. And if you have further questions, do not hesitate to contact me.
Yes, thank you very much, Jan, for the good presentation. And for our attendees, if you have any questions, you can also ask today through the chat box for the Q&A session later. We will now move on to the next speaker, Andrea Ramirez from the Delft University of Technology. And Andrea will talk to us about a system approach of understanding the role of CCUS in industrial clusters. Andrea, the floor is yours. I think you are muted.
I'm trying to share my screen.
You should get a request from Tom, so there should be a message popping up.
So it went into my system preferences. Wait, don't know where it is right now. Sorry about it.
No worries.
It's not in my. Apologies for it. It's not in my menu, Jasmine.
Yeah, let me check.
I sent my presentation. Tom has it. Yeah, look.
Okay.
Apologies to everyone. Happens.
No problem.
You have it?
Tom should have it. It might take a couple of seconds to.
Yeah, apologies for it, but then I do remotely control my screen. I don't know where it is. I should have it. Too many screens, I think. Trying to find it. Yeah.
Ah, there it is.
Perfect. Thank you, Tom. So, yes. Good afternoon, everyone. My name is Andrea Ramirez. I'm professor on low carbon systems and technologies at Delft University of Technology in the Netherlands. And well, it's a big challenge after so many nice and detailed presentations. And I try to look at this a little bit more from a system point of view. But it's very difficult, you know, not to discuss technologies when we are discussing systems. Next, please. So I have three messages or three topics more that I would like to just brainstorm with you and think a little bit about. One is the challenges the CCS has in industry, and I think, of course, Christine and Jan and everyone has been speaking about this one. The second is about whether or not we can reach negativity in the industrial sector, and why I focus on negativity, of course, is highly relevant in the context of the IPCC, but also is highly system and context dependent. So you need to take much more than the technology itself to reach negativity. And that is actually where the main challenge is, in how to manage things that are outside your gate to gate, to call it that, is the part where you have a lot of control. And the third part is, of course, the need to look at different levels and what we call zoom in and zoom out to really understand the potential of CCUS in industry. So can we go to the next, please? So the first thing is there is quite a wealth of experience on CO2 capture or on CO2 transport or in CO2 storage. We have some integrated projects, not as many as we would like to have, given that, you know, how important it is to really move ahead to reach the targets. But a lot of these projects, some of them are industry, but not all of them. A lot of the research actually has not happened into industrial sector, has happened in power sector. So there is a lot of experience and lessons learned that we can translate, but they cannot be transposed one-to-one. It's not a question of just saying it works here and therefore we just need to copy paste and use it in another sector. Can we go to the next, please? So this is a typical one, and it was, I think Christine referred to it on where is the steam coming from, and it's not surprising. This is a publication we had last year together with SINTEF, not only but a lot of other institutions as part of on the network from the International Energy Agency greenhouse gases. So what we were looking a little bit is, yes, we say we need energy, that is quite clear, but as all of us know, there are different ways. Somebody was saying geothermal. There is the possibility to have natural gas boilers. Depending on your location, people are looking at coal CHP plants, or you can fully go electrify. There's another option that is gaining attention lately, or just go to, you know, an electric boiler to produce steam. Hydrogen is not here, but you can also consider that one. Or, you know, a favorite of many of us, the possibility to look for waste heat, which will have large implications in the cost in a positive sense. So it's not one, it's you know, with a power plant, it's extremely straightforward where your steam could come from. With industry, you have a higher portfolio, which you could argue gives you more flexibility, you could argue actually increases the challenge. Can I go next? And in the same publication, we have taken a look at what does it mean when you are having these sources of steam. And what you see in the figure down is just CO2 avoidance cost. So in terms of euros per ton of CO2 avoided in different scenarios. And what is changing in that scenario is not only what is the source of your heat for the steam, so where it's a natural gas boiler or low pressure steam extraction or electric boiler, but we also at different natural gas prices and different electricity prices and a different carbon grid, so electricity CO2 emissions. And just to try to understand how would that affect benchmarking, of course, you see right away a main difference when you have an electric boiler between, you know, a low and high natural gas price. So the natural gas boiler versus the electric boiler, you see quite the difference. You can argue this is green electricity and at what price, and a main issue, of course, what we want to do with green hydrogen and with green electricity and everything that comes from intermittent sources is actually intermittency. So you want to guarantee 24/7, which is the kind of operation that we have in cement or we have in steel. Those system costs of storage to guarantee that you have 24/7 electricity, hydrogen, heat at the quality that you require will increase the cost of that service. So that's something to also take into account. May I go next, please? So one of the things when I especially discuss with a lot of people about the possibility to having CCS in industry, people keep referring to steam, to the waste heat. And I think for all of you who work on industrial sectors or who are trying to do this analysis, we don't know what waste heat is available until you are going to go and look for it. So in the moment you really have a project and you have a location and you have a setting and you come from this idea of I will find waste heat and that will make my CCS process quite feasible, then you go to look for it and you realize, well, it may be there, but not of the quality, of the quantity, of may not be there at all. So this is an assessment, and apologies, I cannot show you the companies, but it's on their NDA, that we have done for the Port of Rotterdam regarding the possibility to have mineralization. And we work with real companies in different locations, so we need the heat. And the first question we did was, to identify the heat of the 5 companies. There were one who has not all the heat but some heat available. The other 4 companies did not have waste heat available that we could use. So what you see on the scenario 1 is the CO2 avoidance. So in the moment we did just the scenario saying, well, there is no waste heat available, so we are only going to use the heat which is rather fossil in this moment. If you use energy from the grid, if we just use heat that we have available at this moment in the port, which is fossil based. So only in the company that have waste heat, we saw actually a decrease on CO2 emissions at normal level. Actually, for the other, we were actually producing more CO2 that we were storing. So that points out that the need of really guaranteeing low sources or low carbon sources of heat and electricity as a condition for a lot of the CCU technologies, you want to call it like that. And of course, once you arrive to these results, the next step that you take unconsciously is that you go on there as a group and say, well, and then you see in the figure below, you have this scenario 1 where you see there is a lot of our CO2 emissions in that scenario that were produced actually from using natural gas in the dryers or from the low pressure steam. Say, what if we have green hydrogen? Then we put heat hydrogen into the picture, and that is scenario 2. It's still too high, guys. What if we also have green electricity? What if we have, and you began to add conditions to make this sense not only from an economic point of view, but also from an environmental point of view. And we can keep adding until we reach what we think will be a nice footprint, but a nice footprint will have implications at system level. Where is the electricity coming? Where is the green hydrogen coming? Where is it going to be located? What are the system impacts? So my point here, I think, is when there is waste heat available, yes, please, let's use it, but not depart from that as a base case scenario, but be a little bit critical on what the implications are. And as soon as you make an assumption on a low carbon or low electricity source, we need to open the system boundaries to try to understand whether it is really available, and if not, what it will take, and what are then the impacts in the system of taking those. May I go to the next one, please? The other question that is people are asking a lot is, what about going beyond neutrality? What if we want to go into carbon negativity? So my next slide is about, just to clarify what I mean by carbon negativity. Next. So this is from a publication that we published with Samantha Tanser already almost 3 years ago. When are negative emissions? And there are 4 really, for us, basic requirements when we speak about negativity. And it's about the physical remove from greenhouse from the atmosphere. It's not about avoidance, it's really physical removals. the storage has to be, long-term, intended to be permanent. You need to account the full supply chain in order to do the full balance. So a gate-to-gate doesn't work. You really need to expand system boundaries. And then last but not least, of course, you need to extract more than you actually emit. It sounds simple. We have been looking at a lot of cases or information on how people are referring to negative emissions, and generally one of the 4 conditions are not met. Next. So we took a theoretical look in a study, and may I have next, please? And this is one of the, I think, for the industrial sector where we are looking at negativities, of course, the combination of bioenergy and CO2 capture. And not surprisingly, today we have spoken about this quite a bit. So if you look into it, this is just a brief summary of the situation as it was in 2021 on what was the industry, the direct CO2 emissions, the status of biomass use, and the status of CO2 capture in industry today. And these are some of the numbers, but what you can see really the step up that we need to do both in terms of biomass and both in terms of CO2 capture is actually quite high. So there is a considerable amount of fossil emissions that we will have to replace, and we will need to have a large deployment. It's there, but we are, I think, moving maybe too slowly. Next. So what do? We just, and this is an example again of steel, so I don't have to repeat how do we produce steel because we just have a very nice lecture about it. But what we did was not only take the production plant, but say if we were going to use, for instance, biomass, charcoal, that was something also that Piera was speaking in her first study, and this is not from a techno-economic point of view, but more from a system and life cycle assessment point of view. What do we need to take into account? And then you go all the way to the biomass, the transport of biomass, the production of charcoal, the transport of charcoal, together with the transport of iron ore, of wood, of natural gas, so all that goes into the steel plant, and then you move your system boundaries and you include as well, in this case, both the steel and the permanent storage of capture biogenic CO2 and fossil CO2 in a geological formation. Next. So we had a look, and this is just because we were trying to understand, is it, if you don't take into account economics, you will assume that you just could do it. Could we reach negativity? And what we notice right now is that there are different technologies, and you have them there. So whether it's furnace, blast of oxygen furnace today, whether we have HISARNA, whether we have recycling, and we did several scenarios and we did a life cycle assessment for several of them. And you notice that when we reach negativity, it's actually in at the bottom, at the right side of your slide. There you began to see some yellow points at the end, and you began to see negativity. So when do we reach negativity? When we have a lot of penetration of CCS, we have novel technologies, and we have a lot of penetration of biomass. Taking, one of those will still make sense in terms of avoidance. We will not reach negativity. That's one. The other thing is the negativity is relatively close to your point of neutrality, and that, as a system modeler says, is going to be highly dependent on all the assumptions. It's no extreme negativity. It will be very carefully designed change to try to reach that point. Next. This is just an example of some of the sensitivities, and what you see is, as soon as in our example we change the electricity mix, we move the point from negative to positive. The same happens when we take the carbon depth, and for those of you who do not work in biomass, that is, if you will not use the biomass will keep capturing CO2 just naturally as a tree. So it will take some time until you reach that or try to compensate for the amount of CO2 that would have been captured anyway by the forest. So it's called carbon depth. And depending on whether you have a short rotation or a long rotation biomass, your carbon depth will be shorter or bigger, and has a big influence in the negativity of the system. So those are kind of things that you don't just notice by only looking at the technology and your system boundaries, but just by expanding the system boundaries. Next. So this is in concrete, just to show you a different case study. And a question that it seems so simple is, your system boundaries matter? So you have here, and we have in this publication, just trying to see how different system boundaries are affecting the results. It's the same technology, it's the same layout, you just get different values. And this kind of system boundaries here, we plot 5 of them, are system boundaries that we found today reported in literature. Sometimes you really have to be really careful and trying to see exactly where they establish that people are not that transparent sometimes when saying there. And you see that the first column is just your factory gates. Some people only do gate to gate, but suddenly consider the biomass neutral. By considering the biomass neutral, you are kind of expanding your system boundaries, but only for one component, only for the biomass. For the rest, is all carbon negative. Then the third column is what if you take into account the CO2 that is emitted, and you take into account in the upstream and supply chain. So you bring not only the biomass, but you bring the transport, in this case, limestone, everything that you need upstream, you take it in your system boundaries, and you see here in blue, down with a minus 130, that is the net impact of what will happen. And then you have in black what will happen if you don't just unabate it, you don't have any biomass, so it's your reference case. And the last column that you see at the end is when you take into account not only the CO2 that is emitted and transported and the CCS, but you also take into account this is concrete, so going from cement to concrete is not that energy intensive, but you also take it into account. You take into account the demolition, and you also take into account that the CO2, the concrete actually also naturally absorbs CO2 from the atmosphere through weathering. So we have taken that into account, and that is the last column that you look. So yes, it's still negative, but it's a huge difference when doing just taking the minus 206 kilograms of CO2 per ton of cement, that when you only take the second column, where you keep your system boundaries and just consider the biomass as sustainable, which was minus 660. So you are reducing just by really expanding uniformly the system boundaries, you are reducing by a factor 3 the negativity of the system. May I have the next slide? So that is system boundaries matter. The other thing that matters, especially in BECS concepts, is the temporal boundary matters. And that has to do with at what point do you reach parity, at which part you reach negativity. And what you see here is the negativity is not reaching in year 0. It's not because you just take the biomass, put charcoal, and then you will get the negativity. No, in this case, it takes in this study around 15 years before you really reach parity. So it's the system with CCS without biomass compared with the system with only bioenergy or with BECS. So these are the different concepts. And if you look really well at the graph, you only reach negativity after 50 years. In this case, it's very, of course, it's very kind of the type of rotation of biomass that we use here. But our point is, you cannot just look and assume in year 1, you really need to understand the whole timeline, and that is another way of system expansion. Next. Apologies, there is something happening in my phone. The final point I want to say is there is a lot of assumptions about industries, and we treat industries as if they were located in isolated places, green fields, which is not how we have industries today. We have most industries located in industrial clusters. Industrial clusters are highly symbiotic. And therefore, there are challenges, but also synergies that we can use when we implement this kind of decarbonization systems. Next. So just to take you a little bit through what I want to say. Next one, please. Let's assume you have this system. You don't have a plan. that uses fossil raw materials, a chemical plant, produces an intermediate, and then has another process to produce a product that will give you some money. And if you look what we call a vertical evaluation, so you look at the value chain type of life cycle assessment, then you have CO2 emissions. Next. And then what we tend to do today is that we say, well, what if we produce the same product, but then we use biomass and waste heat? Or what if we use biomass and natural gas with a bio-based intermediate? What if we do CO2 utilization and use hydrogen from renewables? So all the time we are looking at this, main product and just trying to replace it. And then we get the system analysis in a vertical evaluation, which each individual system gives you different amount of products or energy required, CO2 emissions. You do a cost comparison pairwise and you say, oh, of this system and this system, let's choose option B, for instance. That will be a way. Now, the argument I'm trying to make is maybe in the next slide, is that this is okay in paper. But when you go to real life, may I have the next one? Then you will notice something, and you will notice that if you go to a specific location, that fossil-based plant was actually, for instance, giving waste heat to the neighbor company. So when you replace the plant, you either put a capture unit who will use the waste heat if it's available, or you are going to put a CO2 utilization unit who requires more energy to produce the amount of product. That waste heat will not be available. You are going to change that in flow. So the question that we have is, what happens with the company that was neighbor to you that was using your waste heat? How are they getting the heat then? Can I get the next one? So this is what we call it a little bit in energy analysis, the unexpected results, or maybe not unexpected if you expand it well enough. So what is happening is that if you are not careful, then you move to the right. I'm almost done, Jasmine. I assume that's also why you're here. You move to the right, the waste heat disappears, and then maybe they will use natural gas, and therefore you are just shifting your emissions. Next. So what I'm having right now, one of our big projects in the group, where we are trying to understand how important it is. And what you have here is a twin model that we have developed already in the group, where we have modeled 20 companies and 54 chemicals. Is based on the Port of Rotterdam. And what you see, the lines that join the different boxes. So every box is a company, is a product, sorry. The boxes is how the main product, in chemicals, we have a lot of A used for B, B used for C, C used for D. This is what you see here. Next. I'm almost done. So this is just assuming, you look at all these boxes. This is, for clarity, an example of the kind. This is our chlorine subcluster. And then you can see every different kind of industry. And for every kind of industry, next, then we have a process model, which has been on Aspen. Next. And this is the level at which we are modeling every one of the boxes that you have here. So that allows us to get energy and mass balances, but that doesn't give you an idea of the interconnection. That gives you just a good idea of how our processes or products being raw materials converted into products. Next. So what we have done in the model as well is that we have gone a little bit detective in the port and tried to understand who is sharing what with whom. And these are all different companies. So we have been trying to see who's sharing air or infrastructure for air, who is sharing waste heat, who is sharing waste water, where is the electricity coming from, where is the steam produced, what is the waste fuel being used, what is the nitrogen. And this is a simplified figure. And my point here is, if you want to decarbonize, if you are going to take one of these and replace it and use something different, at system level, you have to take care of what happened with all those interconnections. And some of them may be important and some of them may be not that important, but we need to know before starting to completely transform things if we want to guide the process towards CO2 mitigation. Next. So what we are doing at the moment, some of the PhDs, is we are taking main products like ethylene, and these are at this moment 54 different ways you can produce ethylene, either from CO2, biomass, and waste. And we will model only 3 routes from here. So do the mapping, have the 3 different routes, develop process models for each of them, and then put them in the twin model and start to look at the impact on interactions. And we are going to do this for 20 out of the 54 products, half of those chemical blocks, half of those specialty chemicals. Next, and that will be my last one. So hopefully by doing that and allowing really to try to see what will be the new infrastructure and how is the flexibility and how do we interconnect and what is circularity, that we can actually answer questions and get a better insight that are closer to the real life of industrial clusters today. And I think it was my last slide. Apologies for taking more time than needed. Next. If I'm correct, this will be the last one. Yes. That's it.
Thank you very much, Andrea, for the very, very detailed and very interesting presentation.
Too detailed, Jasmine, sorry.
No worries. Maybe if Jan can also come on again, then we might not have a lot of time for questions, but we should be able to get one question for each of you. So maybe while we are waiting for Jan to come online, we start with you, Andrea. There was a question, why is everybody looking at amine-based technologies and not as much at fully electrified technologies, for example, membrane CO2 capture?
Yeah, it's a question we receive quite frequently. I can say what we did for that project. In the last project I spoke about, we are going to have electrified technology, but in the one I show with MEA, with cement, basically, that at this moment is like the one that consumes the most energy, at least on site. So if you can get there an idea, at least in carbon negativity, if you can reach carbon negativity with the technology that theoretically consumes quite a bit of heat and electricity, then in terms of conclusions, if you do get negativity, it's most likely that we'll get negativity with other technologies that outperform it. So in that case, we went very conservative because our goal was to understand whether we could get negativity, not whether that is the most optimal way to get negativity. So it's 2 different kind of questions. But I agree, is in many cases we see sometimes the benchmark being outdated by reality.
Okay, thank you. And then maybe one question for Jan. If we consider like recent increases in fossil fuel prices and also reliance on fossil fuel imports, what impact could it have on European steelmakers in their planned transition from coal-based BF route to a natural gas-based DRI EAF route? Would it push companies to take a more direct leap to 100% hydrogen DRI EAF, or would it maybe spur the industry to rely more on CCUS solutions? I think you're muted.
Me?
We can hear you now. Yes, yeah.
Okay, yeah, okay. That's a good question, Jasmin. But I think the industry at the moment is already taking lots of effort in reducing the usage of carbon, of fossil type of reductants and energy like coals and natural gas. And as I showed, there has been a tremendous reduction since let's say since the 60s, and that also applies in the blast furnace. There we came to more or less to a thermodynamic minimum. And now, let's say, we are transferring the industry to a DRI type of operation where natural gas could be used. But if you do the direct step to hydrogen, which is on our road map at the Tafsteel in Amine, then also, let's say, there should be, let's say, an enormous effort to be put into action to have green electricity available, to have the electrolyzers for green hydrogen. And then, let's say, the hydrogen becomes available for making it used in the DRI shaft.
Okay, thank you, Jan. Yeah, and regarding the hydrogen, there was also one question earlier, whether do you buy the hydrogen from someone else or do you produce it yourself? And would it be blue hydrogen, green hydrogen that you use, or?
At the moment at Tata Steel, we have our own small hydrogen plant on site, but that's used for let's say other applications at the moment. That is for let's say in the rolling and end product area. And at the moment we have an initiative together with the Port of Amsterdam, where we would like to install an electrolyzer on the IJmuiden site, making use of windmill electricity from the North Sea. And that project, that's the Hermes project, which is at the moment ongoing.
Can I maybe, from a system point of view, I think that is one of the key questions to ask at this moment. And I think in a lot of studies, not necessarily Jan, I think they have a project from a bottom-up perspective. A lot of studies are assuming the hydrogen will be there, and it will be here. And it will be here.
I enjoyed your presentation, Andrea, because let's say at the moment you could say that Tata Steel, at least in the Netherlands, is completely let's say using all its energy sources available. So we go from coal, natural gas to let's say the works horizon gases, and all those gases are applied on site for example, producing electricity or making heat. And when you come in this transition type of discussion, then all of a sudden the blast furnace gas will not be available anymore, and that means that we have to find other sources for, let's say, for heat or for electricity production. So it's also on the steel making side. It will need a systematic system approach. Having of course the hydrogen available in a broader perspective than rather Tata Steel on its own.
Okay, I think in the interest of time, we need to move on. We now have a small break scheduled where everyone can refresh themselves. So we will come back here to start with the last session in about 10 minutes time.
Thank you, Yasmin.
Okay, thank you, Yasmin.
Yeah, thank you too. So welcome back, everybody. We will now start with the last session for this workshop. And the first presentation will be a combined presentation from Emily Supari and Oona Kata-Yisto from VTT Finland. And they will tell us about the reduction of industrial CO2 emissions by electric calcination.
Thank you, Jasmine.
The floor is yours.
My name is... Okay, thank you, Jasmine. I hope you can hear me well and also see my presentation now.
Yes, we can hear you and see your slides.
Great. So my name is Emily Supari and I work at VTT, Technical Research Center of Finland, as principal scientist. And we will give this presentation together with my colleague Oona Kata-Yisto. The topic is reduction of industrial CO2 emissions by electric calcination. And I will start by presenting this concept and some background, and Oona will continue then going deeper to industrial applications and results that we have gained so far with our pilot scale facility. There was some background already in Kristin's presentation. Thank you for that. You made my work a bit easier. But I repeat a bit that limestone is one of the most used materials in the world, and it's responsible for about 3 gigatons of CO2 emissions globally annually. The most important application is cement production, but it is used also significant amounts in burnt lime production needed for steel production, for example, and in pulp and paper industry as well. And we know that at the moment, costs of CO2 emissions are increasing. For example, in Europe, emission allowance price in EU ETS is quite high, almost 100 euros per ton, and fuel prices are unstable and increasing. And on the other hand, there is demand from customer side to have carbon neutral raw materials and carbon neutral products. This reaction was already in Kristin's slides, but this is the basic emission intensive reaction in limestone applications. Of course, the reaction in a cement kiln is much more complicated, but this is the main reason for CO2 emissions there in a calcination part of the process. So calcium carbonate is heated up to 1000 degrees of Celsius or even more, and calcium oxide and carbon dioxide are produced. So this CO2 is unavoidable emission there. It cannot be avoided with process efficiency or something because it's in the raw material. In our concept, we are replacing that heat production by electricity. So we avoid almost half of the emissions immediately because we are not burning anymore. And in addition to that, we don't have flue gases anymore. We don't dilute this raw material based CO2 with flue gases, but we will have very high CO2 concentration in our off gas. It's almost pure CO2. Here we have some examples of the recent development in emission allowance price in EU ETS and a natural gas price in Europe. There is significant increase in both making this kind of electrical solutions more feasible. And please note that these pictures are taken before this crisis in Ukraine, so that increase in prices is not even included here yet. Also, electricity price is following energy prices in Europe. This is from Finnish market area. There is some increase in electricity prices in previous year, but not that huge that in natural gas price or CO2 emission allowance price. You can also see this volatility in electricity prices, which is important to take into account when designing this kind of new electric concept, that if we can provide some flexibility to markets, it can be a significant economic benefit for the concept. But most important when we are talking about climate change mitigation is that carbon emission intensity of electricity in Nordic countries is quite low already and decreasing all the time. And when we think a significant increase in electricity consumption, we can take into account that if we increase the consumption, we need to invest in new production as well, and we don't know what is that impact in system level, but it's probable that it will be low carbon, mostly low carbon investments in new production. In Nordic countries, probably wind power is the main way to increase electricity production. And that's why we have created this project in Finland called Decarbonate. VTT is coordinating this project, and on the right hand side you can see the pilot infra, where we are combining 3 different pilot scale reactors. We have this electrically heated rotating kiln. It was supplied by Kumera, and under it we can see PEM type electrolysis, by which we can produce hydrogen, and we combine carbon dioxide and hydrogen in our CO2 synthesis unit, which is also mobile, and we are using Ineratex technology for Fischer-Tropsch based synthesis in this reactor. So by that we can create carbon neutral fuels. And we have a very good group of companies as partners in this project. We have companies from cement production, steel production, lime production, energy companies, pulp and paper companies, equipment suppliers, and so on. So this is a good group to make things forward. And please, Oona, continue from industrial applications.
Thank you, Emily. So as said, my name is Oona Katajisto and I work as a research scientist at VTT, and I will shortly tell you about the applications that the concept that Emily just presented can be used, and then the pilot kiln. I will present the pilot kiln that we have at VTT. So this concept can directly be used for burnt lime production, and here you can see in the graph the burnt lime production volume in year 2019, and as thank you. Yeah, so for the cement production, the CO2 emission reduction potential is even bigger than for lime production. However, in the cement production process, this concept will only replace the precalciner instead of the whole cement kiln. So the clinker phase formation requires higher temperatures than this electrically heated kiln can reach. And as there will be two separate flue gas flows, there will also be requirement for heat integration. So there will be the almost pure CO2 flow from the electrically heated kiln, and then the normal flue gas flow from the clinker production, or the clinker kiln. And the third example that we have here is a pulp mill. In pulp mills, lime is used in the chemical recovery process, more specifically in the causticizing. And in this case, also the lime kiln can be directly replaced with the electrically heated one. And in this case, the CO2 is mostly biogenic, which is notable. But then we have this pilot scale electrically heated kiln at VTT, which you can see in this picture. The actual rotating drum is positioned inside the sea container, so you unfortunately cannot see it. But what you can see is for example, the output silo under the sea container on the left side, and a similar input silo is positioned above the sea container behind the staircase, which you cannot either see, but the material flows from the input silo through the feeders to the rotating drum, where it's heated with the electrical heating elements, and the drum is located divided into 4 heating zones, which can be individually controlled. And the material heats up in the kiln, and then the calcination reaction takes place in the end of the drum, and then the material drops to the output silo. The drum is 9 meters long, and the diameter is 60 centimeters, and the system height is the whole system height with all the staircases and silos is around 8 meters. And the capacity of the kiln is over 100 kilograms per hour of lime product, and the power capacity is over 300 kilowatts. And the composition of the gas can be analyzed continuously during the experiment run, and also samples of the solid output material can be taken at any time during the experiment run. And here are the first results of the experiments that we have so far performed with this kiln. We have performed this experiments for crowned limestone, and here you can see the remaining CO2 in the lime product that we produced with this kiln. And the best result we reached was 0.7 weight percent in the product, which equals to around 98% degree of calcination. So we had several test points with different material flows of raw material, different temperatures, and then we also varied the drum rotation speed. What is notable is that the degree of calcination increased when the drum rotation was increased as well. And this means that the heat transfer improved in the drum and the material bed moved more efficiently. And in addition to degree of calcination, we also got results of the gas composition on the next slide. Thank you. So we reached really high CO2 levels in the off gas from the kiln. I think the highest was 98 degrees percent. And here you can also see the relation between CO2 level and oxygen level in the raw off gas. And what we observed was that the CO2 level in the off gas is mainly dependent on the air ingress to the kiln, and we can actually control the air ingress to the kiln, and thus we can control also the CO2 level in the output gas. So to sum up the first observations from the experiments we have done so far is that we reach really high CO2 content in the kiln of gases and also sufficient degree of calcination. We were able to operate the kiln continuously at high temperatures of around 1000 degrees of Celsius for 4 days at each time and without no shutdowns or major availability issues. So it's looking really good. And that's all we have to tell you today. And I would like to thank you for your interest in listening to our presentation.
Yes, thank you very much, Ona and Emily, for this presentation. And we go ahead with the next presenter, who is Fabian Levin from Stockholm Exergy. Hello, Fabian.
Hello. Hi. I think you can hear me, I hope.
We can hear you. Yes, positive.
Yes.
We can
so
also
yes.
see your screen. Yeah.
Yes. Then you would like, now you maybe can see my presentation.
Now we can see the slides. Yeah. Perfect.
Yes. Perfect. Thank you very much. Yes. So my name is Fabian Levin, and I'm head of R&D at Stockholm Exergy, which is the main utility in the city of Stockholm. We operate mainly district heating, district cooling, electric power production, and also incineration of waste. We have some 60 production units of all of these things dispersed around the city of Stockholm, with major production units in combined heat and power based on, we have a few on waste incineration and some on biomass. And also we have the world's biggest and the world's next biggest heat pump installations. We have the largest one have a combined capacity of 251 megawatt of district heating from heat pumps, which I think is quite cool as well, utilizing sewage water as a heat source for those. But today I'm going to talk about bio-CCS. In Sweden, we talk a lot more about bio-CCS than BECCS. And the reason, of course, is that besides in the energy sector, there's such a huge potential in the pulp and paper industry as well. So that's why the concept of bio-CCS is more commonly used to sort of give the notion of that it's not only interesting for bioenergy. We know that the world needs negative emissions. From the first working group of the big IPCC assessment report that we're seeing, we know that carbon dioxide removal and anthropogenic carbon dioxide removal is essentially basically the actual word used by in the IPCC report is virtually all scenarios that reach net zero. We need negative emissions in the form of carbon dioxide removal to compensate for the emissions that we can't get rid of. So for a lot of the emissions in the world, maybe 10% or maybe 20% of what we see, we lack good solutions for getting rid of the last greenhouse gases. And that's the reality. And that's also why so many scenarios in the end up in a need for carbon dioxide removal. And that's basically what we're working on Stockholm Exergy, one of our biggest development project at the moment. We also got the Innovation Fund. We were one of the over 400 in the second round 70 that contested for it, and we were one of the 7 projects that was appointed, which of course we are extremely proud of. I think not the least for all the due diligence that sort of put in place. Many of you have seen this kind of curve. This one I borrowed from a paper in The Economist last year. It's data from Goldman Sachs. It shows a marginal abatement cost curve for global greenhouse gas emissions. And this is typically what we see in all of these scenarios, that for the last maybe 20%, 15%, 10%, somewhere around that, differs a little bit between models. When we get to that amount of climate change abatement, so that we have abated maybe 80% or 90%, so we have 10 or 20% left, costs become extremely high. And for the gray part, we altogether lack alternatives for reducing greenhouse gases. It could, for example, be leakage of laughing gas and nitrous oxide from plowing farmland. You can't solve that anyway. And of course, leakage from sewage treatment, landfill for those places in the world that still have landfill. And of course, you have, even if you have a fossil process and you put CCS, you might have 90 or 95% capture rate, which means that you basically still have 5 or 10% of the emissions left, which is too much, provided that we are really looking at net zero targets at the moment. What CDR does, and this is a schematic figure, is basically this. It basically pushes the steep part of the supply curve to the right, the supply curve of CO2 abatement, which basically means that we can reach net zero targets altogether, even though we have emissions that we can't avoid in the end. And it also allows us to reach net zero at a much lower cost. So this is a schematic picture. If we look in this curve, what basically would happen is that we will push the whole curve to the right by including negative emissions. And of course, if these really expensive options of taking away CO2 is in the range of $700 per ton, and we can do BECCS or bio-CCS at $100 per ton. So sorry, if the alternative cost is 800 and we can do CDR at 100, then of course the saving is which basically is cost that will be coming back to economic welfare of nations that can be used for education or for other things. In the end, that basically means that you can save $700 per ton or something like that for reaching the target. The big Danish consultancy firm, they did a study on this recently for what would be the economic impact of doing BECCS in Sweden in relation to the net zero target in Sweden. And they found that Sweden would save some 8 billion euro per year by utilizing 10 million tons of BECCS in relation to its net zero targets. So of course, that's a lot of money, 8 billion euro per year. That's sort of what can be saved or increased economic efficiency by including CDR as a tool to reach net zero. From our review, what makes it really interesting is that all of these processes for capturing CO2, they generate a lot of heat. In our project, our goal is to have full scale by the end of 2025, BECCS on one of our largest combined heat and power plant on biomass. We use forest residues, branches, tops, sawdust and bark. And in the end, capturing CO2 is an exothermic process. We take CO2 from the flue gases that are 44 degrees and we transport it away at maybe -20, which basically means that it is possible to thermodynamically design a carbon capture process if you put it in relation to heat recovery for district heating to actually increase the total efficiency of a combined heat and power plant. In this case, we would lose some electricity production from the combined heat and power plant, but we can recover. So we need about 60 megawatt of electric power to drive the capture process and liquefaction, but we can get more than 70 megawatt of usable district heating from that. So the total efficiency of the plant would increase by 3%. And I should also say, for those not accustomed to combined heat and power, these are lower heating value numbers. So the sort of thermal radiation that you get by incinerating the biomass. And the reason why we get over 100% efficiency in relation to lower heating value is that you also condense the water in the flue gases, which basically means that we get a lot of energy out of the condensation. So it's perfectly possible to build carbon capture in relation to district heating and actually get more energy out than you otherwise would, increasing the overall efficiency of a combined heat and power plant, which I think is quite clever actually. And when I talk to people in England and others, of course, all of this district heating, in Sweden we have district heating systems, same in Finland and other places, but in many places around the globe, and I think the development during the last week makes it even more interesting, because district heating is something that you could replace burning of natural gas for heating homes. So we could capture carbon and we could use the carbon as the carbon capture also as a driver for getting more district heating out that we can use to replace gas, which makes it an even more interesting concept, I think, for continental Europe, where the world is standing today. This is basically how it will look. This is a sketch by some architects on how our carbon capture unit is going to look. We're planning it at Värtaverket in Stockholm, where we have an existing deep sea port, which of course helps quite a lot in this sense. And to verify the technology, we have a research facility. So we have been operating this for now 2 years, and it is a small-scale capture unit where we evaluate the capture technology. And what we're looking at specifically, hot potassium carbonate. Quite unusual when looking in energy to use hot potassium carbonate, but the reason is that it's really good in relation to combined heat and power, because the desorber is operating at 105 degrees Celsius, which essentially means that it can be used. You can basically recover this heating from the desorber only by heat exchanging. You don't need to use a heat pump or anything to pump the heat up even more, which makes the technology. Yes, and I think that's basically what I wanted to share with you today.
Yes, thank you very much, Fabian. If anyone has questions for Fabian, please put them in the chat box, and we will now continue with our last presentation for today, which will be given by Christoph Beutler from Climeworks, and he will tell us about direct air capture, what is the state of play, outlook, and use cases.
Thank you very much, Yasmin. I'm trying to go to full screen. Can you see my screen?
Yes, we can see your slides. Yep.
Is the panel, is the WebEx, the panel still visible or?
No.
No. Perfect.
I'm just seeing
Very
your
good.
slides. Yeah.
That's excellent. Okay, then I can start. So yeah, thank you very much for inviting me, and Fabian, thank you for this excellent presentation. I now can focus on another aspect, the scale up, because you have covered so much of the basics of negative emissions. Nevertheless, I want to go into it from a direct air capture perspective, and as has been said by Fabian and many speakers before me, according to almost all IPCC scenarios, we will need large amounts of negative emissions, basically now, and especially post 2050, where we have to globally enter a period of net negative emissions, and hopefully we can make it to net zero in 2050. But what my point is, we will likely overshoot our carbon budgets, and then we need these negative emissions for three things: to replace fossil carbon for fuels and materials. So a lot of products and fuels contain carbon, so we like to talk about defossilization rather than decarbonization. We heard that before, neutralize unavoidable emissions in order to reach net zero, and then realize net negative emissions. And the key issue here is how do we get to the scales that are needed, that will be needed in time. There are several pathways to negative emissions. We heard from Andrea what true negative emissions are, and we subscribe to that view. I think we need all of them, in addition to more efforts in mitigation. And what direct air capture can bring to the table is that it is very space efficient. So here we have a calculation, a rough calculation of how much land area direct air capture would need to remove 8 gigatons per year, which is kind of a median scenario of what's likely needed in 2050. And this uses PV panels and direct air capture plants, and basically we have two major routes to negative emissions. One is via biomass and one is via technology. And here direct air capture is on a land area the smallest, but it needs energy, and it has to be renewable to keep the footprint down. Our technology is a bit different from other direct air capture companies, and also we think a bit special. Why is that? So it's basically a two-step process. So phase one, we draw ambient air through a filter. That filter is very highly selective and only binds CO2 to it. And then we close the box and heat it to about 100 degrees Celsius. And then we get a stream of concentrated CO2 that we can either utilize or store permanently to achieve negative emissions. And within that heating to only 100 degrees Celsius lies the key of us being able to use renewable energy or waste energy, low-grade waste heat. This is Orca. This is our 15th project. Well, it's actually half of Orca. We opened this in September last year, and it's currently, as usual when we open a plant, the world's largest direct air capture, and in this case storage facility, and it has a scale of 4,000 tons, which is tiny compared to what's likely be needed. So we need to get any of these removal technologies to gigaton scale within 30 years. So this is where we are. We are globally the largest direct air capture company. There are some others that are also trying to build their first plants, and we really root for them because, as I said, we need this to happen fast. Let me go a bit more into detail what Orca does, and then I want to present a use case as well. So what we have developed with our partners in Iceland at Carbfix is basically we take CO2 from the atmosphere and then permanently store it underground via mineralization, because we think this is the safest possible storage option that is also easy to perceive as being safe from a layman's perspective. In the case of Iceland, we use geothermal heat, which even has a smaller footprint than if we want to do it with PV, and we use the heat, which is the main energy requirement, has been said many times before, to run the process from a heat side, and then we use the renewable energy, the electricity, to run the fans and auxiliaries. Let me just say that the process of storing is quite water intensive, but our partners at Carbfix have recently also demonstrated that this can be done using seawater. So we're not relying on fresh water for this, and obviously currently sea levels are rising. So just to quickly outline a few traits of this. So it's obviously permanent. It removes the CO2 from the air immediately almost, and stores it underground, and about 95% of the CO2 mineralizes within 2 years. You can see a bore core at the bottom left, and the white bits are the mineralized CO2. It's also verified already, and it's a commercial service we offer to companies and even individuals. Why is this important? Obviously, you know, we are always, you know, in favor of looking not at the now, but at the net zero case. And if you then look at carbon markets, they will have to change, and I'm using the words on purpose, they will have to change quite a bit, because at net zero there are no more avoided emissions, but there are just emissions and removals. So you cannot rely on avoided emissions, and many companies obviously realize that there's a problem with the supply of these, especially high quality, permanent, easy to measure carbon removal credits, and therefore they're buying these to drive forward the development of direct air capture and carbon removal. Here's a list of some of them. So it basically started in May 2020 with a Stripe, and since then many have followed. The amounts of the purchases have also gone up. We're talking tens of millions now. After Swiss Re, the Bank of Liechtenstein has also done a deal with us, and obviously some of the other companies. So this is going really well, but it is a voluntary market, and that market is only 1 billion globally. And the compliance market, the current compliance market, mainly the EU ETS, has a volume of 860 billion. So in order to grow this into the million ton, the megaton, and then the gigaton scale, this needs to go into the compliance markets. Currently, there's a proposal by an MEP to include BECCS and direct air capture into the EU ETS, but obviously, especially for direct air capture, the price points of the EU ETS are simply too low. So we would strongly recommend to also look at this in order for all technologies to benefit. And one way could be to adapt the innovation fund here to open up a removal-only track. With this, I want to go into carbon utilization, and obviously what direct air capture can offer here is, especially for products that release their CO2 at the end of life, which are many, and especially fuels, and especially in aviation, where we cannot simply replace hydrocarbon chain-based fuels. Direct air capture and obviously all other negative emissions technologies that produce a CO2 stream that is pure offer the possibility to really close the carbon cycle. So instead of reusing fossil CO2 once and burning it and then it's released into the atmosphere, we have the possibility to make this very close to carbon neutral. I say very close because, as I've shown in the slide before, there are some residual emissions, but in theory these could also be neutralized with a removal. So the technology is there. The various technology pathways that we can go, but the name of the game is scale up. Maybe to end with a few examples before I want to give an outlook where we are currently and where the direct air capture industry is. Maybe three examples. I want to illustrate the fuels example, and then go into two more details of products that we have released. So what we can do, and we have demonstrated this in a Horizon 2020 project, is we can take CO2 from the ambient air, combine it with green hydrogen, and then electrolyze it Fischer-Tropsch it, and we can get a drop-in fuel that we can fly in current aircraft. Currently, the engines are only allowed 50% of these e-fuels, but I think Rolls-Royce is from next year on offering engines that can go to 100%. And this is the principle. So we build our hydrocarbon chains with CO2 from the air. Obviously, that process is more energy intensive than we get out of it, but it offers a way of being really carbon neutral, where it's unavoidable to use CO2 that ends up in the atmosphere. What Climax has done before this, we have started to work in niche markets. So two examples. One is we provide CO2 to a greenhouse in Switzerland, and we are delivering to Coca-Cola Switzerland for the bubbles in one of their drinks, a mineral water. Obviously, these are niche markets, but they are ways and were good ways for us to start scaling utilization of CO2 from the atmosphere. So what's the road ahead? So for us, as I said, we just opened Orca, our latest project, which is our 15th plant. So we feel we've done this for 10, 12 years now. We feel we're ready to scale. We want to scale with this technology. And as we speak, we are finalizing the planning for our next plant, which will be roughly 10 times the size of Orca. I can't disclose yet where it will be, but it will also be a storage plant. And then we really want to go into a kind of another 5 to 10 to maybe even 25 scale up. Currently, it's no secret that we're looking into the US here, where the infrastructure bill with the direct air capture hubs now provides $3.5 billion of funding for direct air capture. So the funding is now matching in some places the scale up needs that this technology and others need to have to get to megaton and gigaton scale. With this, I want to end, and I'm happy to take questions. Thank you very much.
Yes, thank you, Christoph, for your presentation. Thank you also our other speakers. And if you could turn your camera on, then we could go through all the combined questions that we received. Okay, maybe we start from the back. So we have some questions on direct air capture. And for example, how specific are the conditions in the underground for the carbonation process? And can this be easily replicated elsewhere?
They are, I'm not a geologist, so I will botch this, but they are quite specific, and we cannot replicate it anywhere on the planet, but in many places all over the globe. And if my mind is right, then I think there's already about 1,200 gigatons of potential for mineralization identified. So the mineralization is not the bottleneck. The bottleneck might be mineralization and storage availability and availability for renewable energy and heat. So obviously, one advantage of direct air capture is we don't have to transport the CO2. We can do it right above the injection site. But in order to do this, we also need renewable energy and heat available.
Yeah, one of the questions related to that was also, well, there is, of course, on the one side, the scalability of the direct air capture process, but what about the scalability of the carbonation or mineralization process? And where's the matchup, and does it match up?
Yeah, I think
so if you would quickly.
Yeah, I think I've answered that question.
Yep.
Mainly, I mean, as I've said, currently there's only one project available for mineralization that is developed. That is the Carbfix project in Iceland. But it is possible to develop many more of this type around the globe.
Yes, and then we of course have some questions about the heat and energy requirement. How much heat and how much electricity do you need per ton of CO2?
Yeah, I've published a paper on this in Frontiers, and so it depends a bit on where the project is and which solvent we use. But the main energy requirement is the waste heat. It's about 3/4 to 1/3, and the rest is electricity. We don't publish our current numbers, but the kind of the midterm, longer term numbers are in the paper, and I think they are about 1,500 kilowatt hours of heat and 500 of electricity.
Mm-hmm. Okay, thank you. Then we also have a question for Fabian. For the last scenario that you presented with the water capture from flue gas and all other elements, what part of it is realistic to be deployed in 2030, and what elements do you think will be more in the 2050 timeline?
Yeah, so I would be happy. I would just like to comment first on Christoph's last question.
Mm-hmm.
I think
yeah, sure.
also the energy for direct air capture could be immensely improved if you started looking at heat recovery. Of course, we could use the heat from direct air capture as well to drive for domestic heating, for creating hot water and hot space. Then for my question, we started installing flue gas condensation, as it's called, when you condense the steam out of the flue gases in 2009. And the combined heat and power part that we're looking at putting backstones to the biomass is fueled by the residues from the forest. That one was commissioned in 2016 and is built with flue gas condensation from the beginning. So that is already sort of common technology in Sweden, at least, and I think in other Nordic countries, at least at the moment. Regarding the other heat recovery from the process, so in Sweden we have a long tradition of utilizing large-scale heat pumps for this heating supply to recapture heat from data centers, from we have even from grocery stores actually in Stockholm. The big grocery stores, we recapture the heat from the freezer rooms. So it's also common technology. Just you apply a heat pump as a cooling machine to create to freeze things. That's also common technology. And our largest heat pumps installations today is, as I said, 251 megawatt in one location. Then we have 248 in the second largest. So we have two really large stations with heat pumps already today. and the amount required for a carbon capture in our case is maybe 30 megawatt. So that's also smaller scale than we already have adopted in our business. So all of this is existing technology. What is new and why we got Innovation Fund is that we are integrating all of these pieces into a combined heat and power plant, and then that to catch carbon. That is new, but all the components and the respective integration into heat energy recovery is existing technology and has been at least for 10 to 30 years, depending on what components we're looking at.
Mm-hmm. Yeah, thank you, Fabian. We also have questions for Emily and Ona. And one is, do you see a future where electric kilns are pressurized and intermittent to save on CO2 compression and peak electricity pricing?
I can take this. It can be possible. I know that there has been some challenges with pressurized reactors when you are feeding solid fuels, and in this case you should feed solid limestone there, so it might be a challenge. But I would actually go to opposite direction, because we have seen that under pressure helps with this reaction. So there must be a lot of optimization to do, and why not? It can be possible as well.
Mm-hmm. And also, what are your scale-up plans? So what will be the next step in terms of capacity?
That's indeed our interest at the moment, to scale this up after good results with a pilot scale. But as Ona said, that this is about 100 kilograms per hour. So it seems to be the upper limit that we can handle at research facility. So the next one should be in some industrial site, and that means that it's also the investment of our industrial partners, and that's why I cannot open those discussions at the moment.
Of course. Then we also have some more general questions, concerns regarding if you have a direct air capture plant, how does this affect the local moisture levels and also local CO2 concentrations regarding the local flora and fauna?
I guess I'll take that. Yep. It's not of any consideration. So maybe you remember the 40,000 ton plant I've shown, and obviously there, because it's a U shape, we had to measure if we will suck in CO2 depleted air into one or the other side of the collectors, and already those few tens of meters are enough to basically remix the whole air again and go to normal levels of concentration. So it's not a concern for plants. I guess we can also turn it around and say that the minute this becomes a concern for plants, we have solved the climate problem, because we have been able to reduce the CO2 level in the atmosphere substantially. So that's not the issue, and yeah, I'll leave it here.
Okay, thank you, Christoph. I'm just going to check if we had any more questions in the meantime. I think this is also for direct air capture. So for Christoph, what is, in your opinion, the level of capacity that should be reached for reducing capture costs at comparable level to lowest cost CCS? So about learning curves that are needed.
Well, we are going after the lowest price we can possibly achieve, and we think that will be, from what we can see where the technology is now, it can be around $100 per ton. But just to be clear, that means we will be in the several in the 100 megaton range at least. So it needs to become an industry. It needs to have several companies and suppliers, and will take a few years. So we don't think this will happen before the 2040s. And it also depends on will technologies like direct air capture or negative emissions technologies get enough of a government push to get to those levels. And I think maybe I want to end with we should stop comparing negative emissions technologies to fossil CCS technologies, because we will need both, but they do different things, as Andrea said, right? One reduces an emission, it prevents an emission to enter the atmosphere. That's fossil CCS, and the negative emissions technology takes CO2 from the atmosphere. So we mustn't infer from efficiencies or cost between the two, because it's entirely different. We're chasing 420 parts per million, and CCS does not.
Okay, and we have one more question for Fabian. Your presentation was a lot about cost efficiency or cost effectiveness, and one attendee wants to know more about energy efficiency and resource efficiency. Maybe if you have a comment on that.
Yeah. So in the combined heat and power plant, we will lose about half the power output. So the existing power output is some 135 megawatt, and we will lose about 60 megawatt of electric power. And that includes everything from capture, liquefaction, and even supplying the chips as they are dockside with electric power. Besides that, as I said, we can recover about 74 megawatt of district heating by driving this process with 60 megawatt of electricity in the end. So the overall efficiency, as I said, would go up some 3% in the end. It's about where we will land. So roughly 3% total efficiency. So in relation to how much biomass we put in and how much district heating and electric power we get out, we would increase the total efficiency with 3%. And I'm sorry, I have my 5-year-old getting back from kindergarten in the background. So, but I think that sort of sums it up.
Okay, and I'm just back checking. We also have one or two more very technical questions for Emily and Ona. So is it possible that you can tell us exactly which kind of electric heating you were using?
We can open that a bit, that it's an indirect heating process. So that's outside of the rotating tube.
Thank you. And the second, also technical question, what amount of false air ingress do you have, or are you considering for the calcination process?
Well, I can take that one. In general, of course, we want as high CO2 level as we can get. But with slight overpressure or slight, what is the opposite of overpressure? Now I'm missing the word.
Under
but
pressure.
Lower pressure, yes, thank you. Yeah, with slight pressure changes, we can, of course, affect the gas atmosphere in the kiln, and thus the air ingress to the kiln. But in general, as high CO2 level as possible.
Okay, thank you. I think that were most of the questions. If there are any unanswered questions, we intend to distribute them to the speakers after the meeting, and we will also kind of publish a small summary of this meeting where some of these unanswered questions then can be attached. But now we want to continue actually with our panel discussion. So I invite all the speakers from today to please turn on their cameras, and also our moderator, who will be Tore Berntsen from IETS, who will moderate this session for you.
Thank you very much. Tom, I would like to show one slide. Can you allow me that? So can you see it now? I think so.
Yes.
Yes. Thanks. Thank you all for impressive presentations and showing us the whole breadth of this area. We could discuss many of these different topics for a long time, but I think that we shall use this half hour to discuss and ask you as panelists about how you see the need for international collaboration in this area, because that is what we are aiming at together now in our two TCPs. And it's also then to how the main question is how to accelerate the introduction of CCUS in process industry through international RD&D collaboration. I have put up here some bullets. I did that before the meeting, but they still hold. I think these are the things we have discussed very much. We have the policy instruments about R&D there, business models needed, investment models, and so on. One main question that many of you have touched upon and discussed is the role of CCUS in an industrial system, and I will come back to different details there later on. We have also discussed industrial symbiosis and circular economy and the use of or the role of CCUS in those. And of course, very much about applications of bio-CCS for negative emissions. And also we have talked about DAC, and the question is DAC in connection with industry in some way. That will be a question to Christoph to use industrial heat or such a thing. That is a question I would have to you also later on. Then also opportunities for CCU, and we have also discussed main alternatives to CCUS. I will first talk about the role of CCUS and ask you about that. As we have seen from Andrea and others, in process industry, it's different in different industry, but in process industry, it's often rather complex situation to put in different CCUS systems as they change the whole energy balances and they different measures and combination of different measures can become lock-in effects, for example, and you have to see this in a system perspective. I would like to ask you first, several of you have discussed that, where do you see a need for further research there and also research internationally and sharing experiences in that area? It's not only a question here about the real research, it's also a question about how to have a better knowledge transfer from researchers to industry to and so on through our different TCPs. Who would like to start there? Andrea, you have worked very much and presented very much about that. Do you have any comments about that?
Andrea, you're on mute.
Are you there, Andrea?
Yeah, now
How can we work together in the area you have? Yes, you have heard me. Yes, please.
Yeah. No, it was me after 2 years. I still don't know how to unmute. No, I was. There are a couple of things. I think one of them is in the area of infrastructure. I think we will need to support industry, there will have to be an infrastructure. And I'm not speaking only about CO2 pipelines. I'm speaking also about, you know, electricity or the hydrogen, and not least the human capital. And that's part of the infrastructure to do transformation. And if you ask a lot, at least when I speak with a lot of people, of course, they are assuming it will be a gate. There are a lot of things that are going to be a gate, but if they are not a gate, if the CO2 is not a gate for do the transformation, if the electricity is not there, if the hydrogen is not there, then it's a huge bottleneck because they are already taking a risk. So this just increases the risk. So infrastructure is one. And I think on the other side, there's a lot of transformation happening. And you speak about the role of sequencing, and we have been also looking at that. So do I put the heat pump first and then my CCS? And do I then transform the core process, or do I do it the other way? And as soon as I put something, does it lock in my next option? And is that lock-in acceptable or not? I think we need to have a better understanding about sequencing, about infrastructure, about not only CO2, but also the other aspects, material availability, critical raw materials, all the issues that you need to take in place to actually deploy. And many of those are systems, and many of those are actually dependent on value chains that are not in place. So we will need to implement those value chains. So it is a complex, and we need to break it in little pieces so it can happen, but we cannot oversimplify the problem, because I think then the solution will not happen. The cost will be off. The impacts will be off. So the main question is, how can we get the basis for promoting investment, the risk in investment, and still trying to understand what are the system changes that need to be in place in order to support people to do transformation. That will be, and that implies that a lot of the people here are doing research, but also a lot of the industry. We need to understand better decision-making process. We need to understand better what are the needs and what are the requirements. I think that will be part of my answer. And if may I, and I don't want to use all the time, so I will shut up after this. We need to stop considering free lunches. And people who know me knows that I use that term a lot. There is a lot of free lunches, assuming that there are things that will be there magically. The CO2, the hydrogen, at low cost in your door to make use of it, and you will get paid for it. And the hard reality is that this is not the case. So if you take out the free lunch out of the invention, then you get the question of how do you get the material there, and at what price, and who pays for it. If you assume there is a free lunch and it's somebody else's problem, then that will not happen. It's always somebody else's problem. We need to stop that and try to build a little bit better systems and larger systems when considering this.
Any other comments about this?
I can just say that I agree with Andrea that there are a lot of things that need to come into place with infrastructure and everything. But I would like to emphasize one more thing that I think Andrea and Philip are very important here, because we need more people who know how to do this. If you look at the magnitude of the problem actually that we need to roll out. So I think you're doing a very important job. But it's just have that said. But it's also about making the implementation affordable, as you also say, Andrea. That it's not like one project, like Fabian. You were one of the lucky winners. You got the innovation fund money. But look at how many projects we actually need to make an impact, and that cannot come from companies having to fight for the money. If we had over 300 projects applying in the first phase, spending a lot of money or time to get, and 7 projects get money from the innovation fund, we can't have it like that. It needs to be rolled out faster. I don't know how, but you can see the need for that. And there's some kind of a structural change that must become, but not a free lunch at the same time.
You said there is a need for people, and I definitely agree with that. Are you talking about research people or reception capacity in industry? Both, I think.
Both, everywhere.
Yeah.
You need to scale up the industrial capacity, the consultants, the engineers
exactly.
in the industries who know how to do this.
Yes. Fabian has raised his hand, and also Philip. Fabian first, please.
Yes, I think it's no sort of secret that we're talking about a big transformation globally, but it's some between 3.5 and 4.5 gigatons in the median of the IPCC scenarios of negative emissions. That's about 4,000 industrial units globally until 2060. That's perfectly feasible to build. Sweden, the potential for Sweden is 40 units, then we would have 30 million tons just from Sweden. So that's getting close to 1% of the global median need in the IPCC scenario. So I think it's perfectly achievable to do, but we need to start. And a way to start is start thinking about it. So we have net zero targets. Maybe we should have quota systems. So if you want to emit a ton of fossil CO2 or other greenhouse gases while we reach the date for the net zero, you need to see to that you have the same amount of carbon dioxide removal from ducts, from biochar, from BECCS or other things in place, or maybe carbon take-back obligation or other of these schemes, because the closer we are to net zero, that becomes the reality that you need to sort of get that under control. And then we can see projects rolling out quite fast.
Philip and then Christoph.
Yeah, maybe following up for Fabian, I think, I mean, a key issue here is, of course, that there is an incentive for both CCS and for negative emissions. And I think what there is a little bit too little studies on, but where I think also the industry will sort of accelerate is when you have this sort of value chain perspective, where you look more at the increased cost of the end product and services for mitigation. I mean, obviously, most societies follow a polluter pays principle when it comes to pricing of the emissions, such as CO2 tax or EU ETS, which is reasonable. And of course, these policy measures are important, but they have a disadvantage, and it is that as a consumer, you wouldn't know if you buy a Mercedes car and it would be of CO2-free steel, how much more expensive would that car need to be? So that I see as a sort of drawback of the polluter pays principle, and because we all are polluters when we consume. So I think this is something that is very important, and we see very positive trends today when many companies who are more in the end of the value chain directly towards consumers have started to market their, it's been a sales pitch to have a climate neutral or even climate positive product. So I think that will accelerate, hopefully. I mean, we see trends on that. So that's one thing which I want to point out. The other one, I think maybe is a bit more in this sense, not negative perhaps, but it is that I think one needs to always have, I brought it up as my very last point in my presentation, about the value of the carbon atoms. And if we take, for instance, waste to energy, where we have plastics, the ultimate goal must be to phase out the production of plastics from new raw oil. And therefore, one also needs to look at circular systems, where there are some projects, which could involve CO2 capture, by the way. But I think that there are also some others. So I think it's always important to not blindly assume that CCS or bio-CCS are the best options. So that's something where there is need for research to look at the long-term sustainability of the handling of the carbon atoms. That would be my more sort of technical point of the research.
Thank you.
It's against the CCS, but it's still of importance.
Christoph? Oh, sorry. You're ready, Philip?
Yes, but I can talk more if you want to.
I don't want you to do that. No, I have heard you before. So, Christoph, please.
Thank you very much, and let me start off by saying that I agree with everything that's been said so far. So yeah, as Fabian said, we need to start, and therefore we need people, and we need people in industry, and obviously people doing research. But I want to say three things. So I think the first thing that we need to understand is the size of the push that is needed to start. And if you look at, for example, the Germany and the way it pushed wind and solar, that cost 150 billion combined to really push these renewables into the German and then the global market, because costs fell. And I think we need something similar here for CDR and CCS. The second thing we need is we need standards that really avoid a race to the bottom and keep things that are separate. Just the technologies in negative emissions, they react so differently, and they are so different in price and in volume they can produce, and scalability and so forth. So we really need to separate these things out. So in one way, I feel often that CCUS is not a helpful term. It should be CCS, CCU, CDR, CDRU, and we should be really clear about the differences, and also protect these differences with a certification mechanism. Luckily, the EU is working on one at the moment, and we really hope it's coming at the end of the year. So we have high hopes in it. And I think the second one is exactly what Fabian already raised. How do we get the system from a world where you can still avoid emissions and you can trade avoided emission certificates, to a world where we in essence have to have carbon take back obligations, right? Where anything we emit, we have to take back. And obviously to introduce that now would cripple the economy. So I want to make a concrete suggestion, and it's exactly the idea of quotas. I think we have to somehow introduce a quota system, for example, in the EU ETS, in compliance markets, where any allowance has a certain amount of removals, because we have to end, in the case of EU ETS, at zero avoided emissions allowance in 2050, and we have to end at a large number of removals. So if we have a quota that takes EU ETS allowances from 1%, containing 1% of removals, to containing 100% of removals, and in 2050, something like that could maybe work. I'll stop here.
Thank you very much. You are talking all so well, so I have problems writing down everything, more or less. Just a short question to you, Christoph. I'm just curious about any options, or have you looked into that, of using industrial symbiosis, connecting your type of equipment to an industry having excess heat, which cannot be used in another way or something? Can you elaborate a little on that? It would be interesting.
Yeah, sure, I can. So the two plants we have in Switzerland, or two of the plants we have in Switzerland, are on top of a waste incineration plant, and we use the waste heat from the waste incineration plant. Yes. In Iceland, we use heat from the geothermal plant. We can go on and use waste heat for a number of years, but that, I mean, in that case, we have to co-locate the storage or the utilization with the renewable energy and the heat. That's possible. But also we should be clear that there will be a time when this goes towards gigaton scale that we probably exhaust the options of waste heat, and we'll have to make our own heat. And that's why we think having a low desorption point is so important. So making our own heat, producing our own heat can be fossil independent.
Yes, thanks. That leads me to another area which I have worked with rather much earlier, and which some of you have mentioned also, the temperature of desorption, how that can be changed. And Christine talked very much about not looking at the given conditions, so to say, but looking at other options there, and so on. And of course, to lower temperature levels can be very much gained, as there is much more excess heat there and so on. Is that an area for international cooperation also, groups working in that area? Is it interesting? What do you say?
Should I
mean,
start?
going below 100, going down to 70 or something. Christine, I think it's for you.
Yes, I can start, but I think it's interesting if you can use low exergy heat for regenerating. But I mean, you lose the the condensation heat from the steam if you just use hot water, of course. And also, if you go down in pressure and temperature in the desorber, you also need perhaps a vacuum pump. So we need more electric power instead. So I think we need to understand more about this. But it could be an area that could need more focus, because there is more low temperature heat available than heat at higher temperatures. It could be some trade-offs there. But it's also the trade-off against what else should you use the heat for, as always.
Any other comment about that? I see Andrea nodding. That it looks as if you're thinking about something.
Yeah, no, you know me. No, I was thinking is you have waste heat, let's assume, of high quality or low quality. The question is what do you use that waste heat for, and where do you get the most result? Is it going to be for industrial symbiosis with residential houses? Is it going to be for direct air capture? Is it going to be for the capture unit? Is it going to do for another for a CO2 utilization unit? That only makes sense. So it's no. And
for
where
heat
do you
pumping?
use it?
For heat pumping. Exactly.
So it's the same with renewables. And we tend to speak about renewables as being infinite source, maybe. But the capex to put the renewables and the time of deployment implies that there is a place where you need to think, where do you use that resources for as a society? Where do we get the most storm? While we get enough, that it will be enough. But there will be a time where there is enough of that. Until then, I will consider it a finite resource, maybe a little bit powder, but it's a finite resource until we have enough of it. And in that time, we need to look as a society where the finite resource for transport, for industry, for electrification for direct air capture and storage, for and of course we need more, and we will be more, but it is a different decision. And if you don't have that available, then what happens with the rest? It's a typical system question that people don't like to ask, but that is being asked at least at the European level as well.
May I give a comment?
Oh yeah, please, Jan, please.
Yeah, I was triggered by Andrea on the free lunch. I'm lucky to have the experience to work for quite a long time in a cooperative international project all over Europe. That was called ULCOS. That was ultra low CO2 steelmaking.
Yes.
And I can say, when we worked on this project, we all thought that at the end of the tunnel, there would be a free lunch, let's say for implementing the technology in the steelworks. And perhaps we also had discussions with the oil industry, we had discussions with the cement industry, and let's say, but at a certain moment everything was developed, and then there was a lack perhaps of willingness to enlarge from, let's say, from a research facility to a pilot or even an industrial demonstration, because then all of a sudden there appeared to be no free lunch, but then someone need to pay the ferryman to go, let's say, to do the transition. And that is at this moment, I think, still happening. And perhaps there are some here and there cases like what Fabian was explaining today. But I think still there need to come instruments for large investments to really lower the CO2 emissions of all kinds of industries we have discussed today. And of course, let's say from our perspective, there is still an enormous need also in the industry for collaboration. And and also, let's say, which is perhaps not being highlighted too much today, also on the U of utilization of CO2 to certain products. Let's say the S, that's more or less established. Let's say in Norway, that is demonstrated that it works. But the next step is perhaps also the U. But unfortunately, I think the U will never be a solution for the complete reduction of CO2 emission. Another thing is the biomass. Is there at the end of the day enough biomass available for all industry? That's also for me a concern. And there also perhaps we say that there is no free lunch.
Thank you. Fabian.
Yes, I think in the end, I think everyone must realize that to solve the climate change issue and reach the Paris agreements, which most countries have stood behind, we will need to get to net zero. So in the end, if they don't solve CCS or hydrogen or something else in the steel industry, there will be no steel industry. And for the ones buying steel today, there will be no steel to buy. That's the harsh reality. They need to solve it, and they need to find a business model to get there in the end. And then regarding the CCU and the CCUS, in the end, the permanence issue is, I think, quite interesting in relation to that. And I think UNFCCC already today, when they regard biomass, if you take out biomass for energy purposes, it's assumed that this gets into the atmosphere directly. For paper, it's 3 years. For wood products, it's a half time of 25 years. And for some board that you use, construction board, it's 30 years half-life in how you estimate the amount of CO2 that's left. My guess is for CCUS, as soon as we get estimates of how permanent it really is, then we can start also regarding how well it works as a solution to create CDR, which also provides incentives for thinking about it in essence. But at the moment, it's sort of lacking that perspective in a lot of discussions.
Thank you. I want to come back to how we can cooperate internationally, and I have seen a number of opportunities, what you have said. And we have also discussed earlier what is true negative emissions from a plant or from a system. And that is not a simple answer always or normally. I think this area is also important for research also internationally, where we can share experiences of case studies, of the methods, how to identify a negative. In some cases it's easy, in some cases, as Andrea has shown, for example, it's not easy at all. And it can be of interest to do that, because it's also important to have a knowledge transfer to industry, to users here in this area. Does anyone agreeing with me? Yes, all. I see that.
If may I,
no?
I think
yes, okay.
the proposal,
I think that is an area where we can work internationally also.
Yeah. And I think it's all, and we have been in that discussion with several of you, with Christopher, what the confusion of using avoidance as negativity, or speaking of CO2 negative at gate. You know, I have a fossil fuel and it's negative at gate. Well, yes, technically, yes. In terms of negativity for IPCC, you have to see where the CO2, the carbon finish, before you can say whether it's negative.
Yes.
So I think it needs to be very careful, because it's already very complex. And the way we are using the terms and telling people who are not necessarily experts on the matter or are not system analysts, and then suddenly with the confusion is going into policies, going into instruments, and it's creating, I think, certainly a field that is very worrisome. I think some of us are worried about it. So I think there is international cooperation, dissemination, understanding of best practices, best cases, keeping the terms separated, understanding what you are speaking. I think that needs urgently to happen before we roll out a lot of things.
Yes, and that's why it's an area where we can work together. I think that could also be included, I think, in what Christoph said earlier about that we need standards, that we need some ways on looking at it. You have raised your hand, but Philip was before you. So Philip and Christoph.
No, I was just thinking that, I mean, I think, of course, if you look back at the CCS history, so to say, since early this century, I mean, there's been research and small piloting for 20 years or so. I think that we're hopefully approaching the first large scale projects, whether it's Fabian's or others. And I think the first project will have an enormous symbolic effect. And after that, one sort of one will be questioned. So you don't have any CCS if you have sort of a chimney with a large flow of CO2. So I think that's very important. Then I think that's hopefully quite soon. Once that is in place, I think again companies will and research will start thinking about the long term, how to allocate carbon atoms, so to say, in there, depending on what value chain they are looking at. So I think that's something that will, once this starts off sort of commercially or driven by incentives, I think there will be a lot happening. But I think that symbolic is very, very important. So that's extremely important that it's finally, hopefully now, happening within, say, 5 years' time, that we have full-scale CCS, which we have not had before, except for some, more dubious EOR applications or so. So I think that's very important.
Thank you, Christoph.
Yeah, maybe I quickly want to come back to the earlier point of the resources and do we have enough? And I think, you know, again, we know where we need to get to. Just yesterday, the second part of the IPCC report was published. We know how urgent it is, and therefore, you know, we really must, I feel, backtrack from net zero and see what we need and how we can achieve this. And also, governments have to, you know, make the money available. I don't want to go into the current crisis, but I mean, we have seen in a number of a few days that, you know, Germany's now planning 100% renewables to become independent of gas imports. Military spending has gone up. So, and the same with the pandemic. I mean, it's possible to do this, and we must remind ourselves what is at stake. It's precisely, if we want to continue to do business, we need stable economies and so forth, and that comes with a stable climate. But I don't want to get too philosophical, but let me bring it back to how can we collaborate internationally. Again, I feel that the mechanism is there. It's the Article 6.2 and Article 6.4 of the Paris Agreement. Luckily, we got the rule book in Glasgow last year, so we have this again, we have a vehicle for to create a robust standard on emissions reductions, negative emissions that can be traded internationally, and we should use it. Thanks.
Yes, and but I still hope and think that industrial collaboration, sharing experiences, having a knowledge transfer in this area can play a role, definitely also. And I hope that we will find a way to work together in this way internationally between our different TCPs. Our time is now, it's time to finish more or less. I will not go through now, summarize what we have said, but I have a list of things that I have written here, and I will put that together. We will have a summary also from our two TCPs that we will do for what we have said now in the discussion and in the presentations. And in that there will be some suggestions for further cooperation internationally based on what you have said now. So I think these inputs have been very interesting, and thank you all very much. And I ask if Jasmine would like to say something in the end. For me, it has been a very interesting afternoon, and I hope that we can find a way to cooperate later on also. Thank you very much.
Thank you. Thank you very much.
Thank you, Dorian. Thank you, everyone.
Thank you.
Thank you for organizing.
Thank
So,
you.
Jasmine, maybe you have something?
Yes,
You're
I
there?
also just want to say thank you to all our panelists and presenters for joining us for this very good meeting. And yeah, as mentioned, the recording and the slides will be made available later. And as Tore mentioned, there will also be a small summary of this meeting, which will be published as an IEA-GHG information paper. So if you are subscribed to our newsletter, you should get a notification when that's being published, or if you follow our social media to keep in the loop. Otherwise, we will send, when the materials are ready, an email to everyone who's registered for this meeting, as we have your emails. So thank you again for joining. Thank you our attendees also for joining, and have a nice rest of the afternoon, day, morning, or wherever you are in the world.
Thank you. Goodbye.
Thank you. Bye.
Thank you. Bye-bye.
Thank you. Bye.
Bye.